Tonight, we embark upon a gentle voyage through the cosmos, where silence reigns supreme and wonder unfolds in slow, magnificent waves. Far beyond the reach of earthly concerns, in the vast expanse of space, phenomena, both beautiful and haunting, have played out their cosmic dramas for billions of years. These are not the violent, chaotic events we might imagine, but rather the quiet, persistent forces that have shaped our universe into the breathtaking tapestry we observe today. As you settle into comfort, allow your mind to drift among the stars. Here, in the peaceful darkness between worlds, we will encounter the most extraordinary phenomena the galaxy has to offer. Each one tells a story of time measured not in minutes or hours, but in millions and billions of years. They are the universe's own lullabies, sung in frequencies beyond human hearing, painted in colors that span the entire electromagnetic spectrum. The cosmic phenomena we will explore tonight are both ancient and eternal. They began long before our solar system formed, and they will continue long after our sun has burned its last. Yet in this moment, as you listen to their stories, you become part of their narrative. Your consciousness, born from the very atoms forged in the hearts of dying stars, connects you to every nebula, every black hole, every distant galaxy we will visit together. Some of these phenomena are violent in nature, yet they unfold so slowly, across such vast scales, that they appear to us as gentle, almost meditative processes. A supernova explosion that releases more energy in seconds than our sun will produce in its entire lifetime appears to us as a slowly brightening point of light, beautiful and serene. A black hole that devours entire star systems does so with such gravitational grace that matter spirals inward like a cosmic ballet, creating some of the most stunning visual displays in the universe. Others are invisible to our eyes, yet fundamental to our existence. Dark matter, which makes up most of the universe's mass, remains hidden from our direct observation, yet its presence is felt in every galaxy's rotation, in every cluster's formation. It is the universe's hidden architecture, the invisible scaffolding upon which all visible matter hangs. Tonight, we will visit the stellar nurseries where new suns are born from cosmic dust and gas, their formation a process so gradual that it spans millions of years. We will witness the spectacular deaths of massive stars, whose final moments seed the cosmos with the elements necessary for planets and life. We will venture near the event horizons of black holes, where space and time bend in ways our everyday experience cannot comprehend. We will explore the mysterious force known as the Great Attractor, pulling our entire local group of galaxies toward an unknown destination. We will marvel at quasars, the most luminous objects in the universe, powered by supermassive black holes at the centers of distant galaxies. We will encounter rogue planets, worlds that wander the cosmic deep without the warmth of a parent star. And we will contemplate the vast voids between galaxy clusters, where emptiness itself becomes a cosmic phenomenon. As we journey together through these wonders, remember that each phenomenon exists in perfect harmony with all others. The universe is not a collection of separate, unrelated events, but rather a single, interconnected system, where every star, every galaxy, every particle of dark matter plays its part in a cosmic symphony that has been playing for nearly 14 billion years. Let the gentle rhythm of cosmic time wash over you. Allow the vast scales of space and time to put your daily concerns into perspective. In the face of such immense beauty and mystery, we find not insignificance, but connection. For we are made of star stuff, born from the same cosmic processes we will explore tonight. The beauty of cosmic phenomena lies not just in their grandeur, but in their patience. While human life unfolds in decades, cosmic events unfold across geological and astronomical timescales that humble our perception of permanence. A single rotation of our galaxy takes 225 million years, a period so vast that the last time our solar system was in its current galactic position, dinosaurs had not yet evolved on Earth. Yet this rotation is just one heartbeat in the life of the Milky Way, which has completed only about 60 such rotations since its formation. Consider the light that reaches us from distant galaxies. Photons that began their journey when the universe was young, traveling for billions of years through the expanding cosmos to finally enter your eyes tonight. In a very real sense, when we look at the night sky, we are looking backward, through time itself. The stars you see are not as they are now, but as they were years, decades, centuries, or millennia ago. The most distant objects we can observe show us the universe as it existed when it was just a fraction of its current age. This temporal displacement creates a profound meditation on the nature of existence itself. Every point of light in the night sky represents not just a distant sun, but a moment frozen in cosmic time. The red giant star Betelgeuse, visible to the naked eye in the constellation Orion, may have already exploded in a spectacular supernova, but because it lies 700 light-years away, we will not see that explosion for hundreds of years. In the cosmic sense, the present moment is not a single point in time, but rather a collection of countless moments from across the universe's history, all arriving at your consciousness simultaneously. The phenomena we will explore tonight operate on scales that stretch our comprehension in every direction. In size, they range from the infinitesimal, quantum fluctuations in the fabric of space-time itself, to the incomprehensibly vast galaxy clusters stretching across hundreds of millions of light-years. In time, they span from the briefest moments, the formation of particle pairs in the vacuum of space, to processes that will continue long after our sun has cooled to a cold, dark ember. Yet within this vast range of scales, patterns emerge. The same fundamental forces that govern the behavior of atoms also shape the largest structures in the universe. Gravity, which keeps your feet planted on Earth, also sculpts spiral arms in galaxies and creates the cosmic web of dark matter that serves as the universe's backbone. Electromagnetic forces, which allow atoms to bond into molecules and molecules into the complex chemistry of life, also power the most energetic phenomena in the cosmos, from the aurora borealis dancing in our planet's magnetosphere to the brilliant jets of material streaming from supermassive black holes at galactic centers. As we prepare to begin our journey through these cosmic wonders, take a moment to appreciate the profound interconnectedness of all things. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was created in the final moments of a stellar explosion. The oxygen you breathe was released by ancient stars as they exhausted their nuclear fuel. You are not separate from the cosmic phenomena we will explore. You are made from them, and you carry their legacy within every cell of your body. This connection extends beyond the merely material. The same physical laws that govern stellar evolution also govern the biochemistry of your brain as you process these thoughts. The thermodynamics that drive stellar fusion also powers the metabolism that keeps you alive. The quantum mechanical processes that determine how atoms interact in the cores of stars also determine how neurons fire in your mind as you contemplate the universe's mysteries. Tonight, as you drift towards sleep, you will be accompanied by the gentle presence of cosmic phenomena that continue their ancient work. While you rest, stars are being born in distant nebulae, their first light beginning journeys that may not end until long after human civilization has evolved into something unrecognizable. Black holes are slowly consuming matter, their event horizons marking boundaries where our understanding of physics reaches its limits. Dark matter continues its invisible influence, maintaining the large-scale structure of the universe through gravitational forces we can measure but not directly observe. The haunting beauty of these phenomena lies in their remoteness and their persistence. They are utterly beyond human influence, following laws and timescales that dwarf our terrestrial concerns, yet they are intimately connected to our existence. They remind us that we live within a universe far grander and more mysterious than our daily experience suggests. Yet they also confirm that we belong to this universe as completely as any star or galaxy. So close your eyes when you feel ready and let your imagination soar among the stars. The universe is vast, ancient, and full of wonders that continue to unfold even as you rest. In the gentle darkness of space, illuminated by the soft glow of distant suns, your cosmic journey begins now. Let the rhythm of cosmic time slow your breathing, Let the vastness of space expand your consciousness, and let the beauty of astronomical phenomena carry you gently into the realm of dreams, where the boundaries between self and cosmos dissolve into peaceful unity. In the vast expanse of space, where darkness seems to reign supreme, there exist clouds of gas and dust so magnificent that they appear as brushstrokes of color across the cosmic canvas. These are the nebulae, the stellar nurseries where new stars are born, in processes so gradual and gentle that they unfold over millions of years like a cosmic meditation. The word nebula comes from the Latin word for cloud, and indeed, these cosmic formations share certain characteristics with the clouds that drift across Earth's sky. Yet where terrestrial clouds are composed of water vapor and exist for mere hours or days, nebulae are vast collections of hydrogen, helium, and heavier elements that persist for millions of years, slowly condensing under their own gravity until they reach the critical density needed to ignite nuclear fusion. Consider the Orion Nebula, one of the most photographed objects in the night sky. Located approximately 1,344 light-years from Earth, this stellar nursery spans roughly 24 light-years across, a distance so vast that light, traveling at 186,000 miles per second, takes nearly a quarter century to cross from one side to the other. Within this seemingly serene cloud of glowing gas, hundreds of new stars are being born, their formation a process so slow that it would appear completely static to human observation, yet so dynamic that it reshapes the very structure of our galaxy. The birth of a star begins with the subtlest of disturbances. Perhaps a nearby supernova sends shockwaves through the nebula, or the gravitational influence of a passing object creates slight variations in density. These tiny irregularities, no more dramatic than gentle ripples on a cosmic pond, begin to attract surrounding material through the inexorable pull of gravity. Over hundreds of thousands of years, these small clumps grow larger and denser, drawing in more and more of the surrounding gas and dust. As the protostar continues to collapse under its own gravity, the material at its center begins to heat up. The gravitational potential energy of the infalling matter converts to thermal energy, and the temperature at the core rises steadily. When the temperature reaches approximately 10 million Kelvin, a threshold is crossed that transforms the collapsing cloud into something entirely new. Nuclear fusion begins, and a star is born. The Eagle Nebula, home to the famous Pillars of Creation, demonstrates this process on a scale that staggers the imagination. These towering columns of gas and dust stretch for light years, sculpted by the stellar winds of young, hot stars that have already formed nearby. The pillars themselves are sites of ongoing star formation, where dense knots of material continue to collapse and condense. The irony is beautiful. The very stars that illuminate and shape these pillars are also slowly eroding them, their intense radiation and stellar winds gradually dispersing the material that gave them birth. Within the Pillars of Creation, astronomers have identified numerous EGs, evaporating gaseous globules, small, dense knots of material that represent stars in the earliest stages of formation. These objects, each roughly the size of our solar system, are cocoons of gas and dust that will eventually give birth to new stars. The process is so slow that these EGs have maintained their essential structure for thousands of years. Yet they are dynamic systems where material continues to collapse inward while outer layers are stripped away by radiation from nearby stars. The colors we observe in these nebulae tell stories of stellar alchemy. The deep red hues that dominate many nebula images come from hydrogen atoms that have been energized by ultraviolet radiation from nearby stars. When these atoms return to their ground state, they emit light at a specific wavelength that appears red to our eyes. The blue and green regions often indicate the presence of oxygen, while other colors reveal the signatures of nitrogen, sulfur, and other elements created in the hearts of earlier generations of stars. The Rosette Nebula exemplifies the cyclical nature of stellar birth and death. This beautiful cosmic flower, located about 5,200 light-years from Earth, was hollowed out by the stellar winds of massive stars that formed at its center. These stars, born from the nebula's own material, now illuminate the remaining gas and dust with their intense radiation. creating the characteristic red glow of hydrogen emission. The central cavity, blown clear by stellar winds, is surrounded by denser regions, where new stars continue to form, ensuring that the cycle of stellar birth will continue for millions of years to come. The Horsehead Nebula presents a different aspect of stellar birth, a dark nebula silhouetted against the bright emission nebula behind it. This iconic cosmic landmark is actually a dense cloud of gas and dust that blocks the light from the glowing hydrogen behind it. Within this dark cloud, temperatures are extremely low, just a few degrees above absolute zero, creating conditions where molecules can form and exist in the harsh environment of space. These molecular clouds are the densest regions of nebulae, and it is here that the initial stages of star formation are most likely to occur. The process of stellar birth is not uniform throughout a nebula. Different regions have different densities, temperatures, and compositions, leading to the formation of different types of stars. The most massive stars, dozens of times more massive than our Sun, form in the densest regions and burn through their nuclear fuel quickly, living for only millions of years before exploding as supernovae. These brief but brilliant lives have a profound impact on their surroundings, creating the very shockwaves that can trigger new rounds of star formation in neighboring regions. Medium-sized stars like our Sun form in less dense regions and enjoy much longer lifespans, burning steadily for billions of years. The smallest stars, red dwarfs with masses less than half that of our Sun, form in the most marginal conditions and can continue shining for trillions of years, longer than the current age of the universe. The Crab Nebula offers a glimpse into the ultimate fate of some nebula processes. This expanding cloud of gas and debris is the remnant of a supernova explosion observed by Chinese astronomers in 1054 CE. The explosion was so bright that it was visible during the day for 23 days. Yet the nebula we observe today is the gentle, ongoing expansion of the stellar material ejected during that catastrophic event. At the center of the Crab Nebula lies a pulsar, a rapidly rotating neutron star that is all that remains of the original star's core. This stellar death, violent though it was, has enriched the surrounding space with heavy elements created during the star's lifetime and in the final moments of its explosion. These elements, carbon, oxygen, silicon, iron, and many others, will eventually become part of new nebulae, where they will be incorporated into the next generation of stars and planets. In this way, the death of one star enables the birth of countless others, each carrying within it the legacy of stellar generations that came before. The study of nebulae reveals that star formation is not a random process but follows patterns influenced by the large-scale structure of galaxies. Spiral arms where gas and dust are compressed by density waves are sites of enhanced star formation. The beautiful spiral structure of galaxies like our own Milky Way is maintained in part by the ongoing cycle of stellar birth and death that plays out within these cosmic clouds. The Cat's Eye Nebula presents yet another chapter in the story of stellar evolution. A planetary nebula formed when a dying star expelled its outer layers into space. Despite its name, planetary nebulae have nothing to do with planets. They received this designation because early astronomers thought their round, disc-like appearance resembled planetary discs when viewed through primitive telescopes. The Cat's Eye Nebula, with its intricate knots and jets of glowing gas, represents the beautiful death throes of a star similar to our Sun, a preview of our own star's fate billions of years in the future. The central white dwarf star in the Cat's Eye Nebula, no larger than Earth but containing roughly half the mass of our Sun, continues to illuminate the expanding shell of gas it expelled during its final stages of evolution. The complex structure of this nebula, its braided knots, symmetric jets, and concentric shells, suggests that the dying star underwent multiple episodes of mass ejection, each creating a new layer in the expanding cosmic sculpture. In the constellation of Cygnus, the North America Nebula stretches across an area of sky 4 times the size of the full moon. This vast emission nebula, located about 2,000 light-years from Earth, owes its distinctive shape to the obscuring effects of interstellar dust clouds that block portions of the glowing hydrogen behind them. The Gulf of Mexico region of this nebula is particularly dark, creating the familiar continental outline that gives the nebula its name. Within the North American nebula, the Pelican Nebula continues the story of stellar birth. This neighboring emission nebula, separated from the North American nebula by a dark lane of dust, contains active star-forming regions where young, hot stars illuminate their surroundings with intense ultraviolet radiation. The interplay between these newborn stars and the surrounding gas creates a dynamic environment where stellar winds carve cavities in the nebular material while triggering new episodes of star formation in compressed regions. The Veil Nebula complex in Cygnus tells a different story, that of stellar death and renewal. This enormous supernova remnant, spanning 6 times the diameter of the full moon in our sky, is the expanding shockwave from a star that exploded between 5,000 and 8,000 years ago. The original supernova would have been visible to the naked eye, appearing as bright as the crescent moon for several weeks before gradually fading from view. Today, the Veil Nebula continues to expand at speeds of approximately 350 kilometers per second, sweeping up interstellar material and heating it to temperatures of millions of degrees. The beautiful filamentary structure we observe results from the interaction between the supernova shockwave and variations in the density of the surrounding interstellar medium. Where the shock encounters denser regions, it slows down and becomes visible as bright filaments of glowing gas. The Flame Nebula, adjacent to the famous Horsehead Nebula in Orion, demonstrates how massive stars influence their stellar nurseries. The central star illuminating this nebula is Alnitak, one of the 3 stars in Orion's belt. This blue supergiant, roughly 800 light-years from Earth, pumps out enormous amounts of ultraviolet radiation that ionizes the surrounding hydrogen gas, causing it to glow with the characteristic red color of hydrogen emission. The temperature contrast within these nebulae is remarkable. While the ionized gas regions glow at temperatures of thousands of degrees, the dark dust lanes can be as cold as -440 degrees Fahrenheit, just a few degrees above absolute zero. These cold, dense regions are where complex molecules can form and survive, including organic compounds that may serve as the building blocks for future planetary systems. The Lagoon Nebula showcases the diversity of stellar birth environments. This bright nebula in Sagittarius contains both emission regions, where hydrogen glows red under the influence of nearby hot stars, and reflection nebulae, where dust particles scatter the blue light from embedded stars, much as Earth's atmosphere scatters sunlight to create blue skies. The dark lane that bisects the Lagoon Nebula is a dense cloud of dust that blocks the light from the glowing gas behind it, creating a striking contrast that gives the nebula its distinctive appearance. Within the Lagoon Nebula, the Hourglass Nebula demonstrates the complex structures that can arise during star formation. This small, bright region contains a young, hot star surrounded by an hourglass-shaped cavity carved out by stellar winds and radiation pressure. The symmetry of this structure suggests that the central star may be part of a binary system, with gravitational interactions shaping the flow of material around the stars. As we contemplate these stellar nurseries, we witness the universe's continuous process of renewal and transformation. The atoms of carbon, oxygen, and nitrogen that were forged in the hearts of ancient stars have been dispersed into space, where they now participate in the formation of new stars and planetary systems. Some of these heavy elements will eventually find their way into rocky planets, where they may become part of the complex chemistry that enables life to emerge and flourish. The nebulae represent patience on a cosmic scale. The processes of stellar birth unfold so slowly that millions of human generations could pass without detecting any visible change in these cosmic clouds. Yet within their apparent stillness lies constant motion, gas flowing along magnetic field lines, dust particles growing through accretion, gravity slowly but inexorably drawing matter together until the critical moment when nuclear fusion ignites and a new star begins its journey through the cosmos. In the gentle glow of these cosmic clouds, we find not violence, but serenity. The birth of stars, though powered by nuclear forces that dwarf any terrestrial phenomenon, appears to us as a peaceful process of gradual condensation and gentle illumination. The nebulae beckon us to expand our conception of time, to appreciate processes that unfold over geological ages, and to find beauty in the vast scales of cosmic architecture. As we drift through these stellar nurseries in our imagination, we are witnessing the continuation of a process that began billions of years ago and will continue for billions of years to come. The nebulae we observe tonight are not static monuments to cosmic beauty, but dynamic systems where the future of our galaxy is being written in the slow collapse of gas clouds and the gentle ignition of nuclear fire. In these cosmic clouds, life begins, hidden within the gas and dust, waiting for the moment when gravity's patient work finally reaches the threshold where matter transforms into energy and a new star adds its light to the cosmic symphony that has been playing since the dawn of time. In the grand theater of the cosmos, few events match the spectacular finale of a massive star's death. A supernova represents the most energetic explosion that occurs naturally in the universe, releasing more energy in a few seconds than our sun will produce over its entire 10 billion year lifetime. Yet for all their violence, these cosmic catastrophes unfold with a kind of majestic inevitability, the final act in a stellar drama that has been building for millions of years. The story of a supernova begins not with death, but with life, the nuclear life of a massive star. Stars with masses greater than 8 times that of our sun live fast and die young, burning through their nuclear fuel at prodigious rates. While our sun will shine steadily for 10 billion years, these stellar giants exhaust their fuel reserves in mere millions of years, racing through their evolutionary stages like cosmic sprinters approaching an inevitable finish line. During its lifetime, such a star operates as a delicate balance between two fundamental forces: gravity, which seeks to collapse the star under its own immense weight, and radiation pressure from nuclear fusion, which pushes outward against gravitational compression. For most of the star's life, these forces remain in equilibrium, maintaining the star's stability. But as the star ages, this balance becomes increasingly precarious. The nuclear fusion process that powers massive stars operates like a cosmic onion, with different elements fusing in successive shells as the star's core temperature rises. Initially, hydrogen fuses into helium in the star's core. When the hydrogen is exhausted, the core contracts and heats up until helium begins fusing into carbon and oxygen. This process continues through successive stages: carbon fusing into neon, neon into oxygen and magnesium, oxygen into silicon, and finally silicon into iron. Iron represents the end of the road for nuclear fusion. Unlike lighter elements, iron cannot release energy through fusion. Instead, fusing iron requires energy input. When the star's core becomes dominated by iron, the nuclear fires that have sustained the star for millions of years begin to falter. Without the outward pressure of fusion reactions, gravity finally gains the upper hand, and the stellar core begins its final, catastrophic collapse. The core collapse happens with breathtaking speed. In less than a second, a core roughly the size of Earth, containing more mass than our sun, collapses to a sphere only 12 to 15 miles in diameter. The matter in this collapsing core becomes so dense that atomic nuclei are crushed together, and electrons are forced to combine with protons to form neutrons. The result is a neutron star, a city-sized object so dense that a teaspoon of its material would weigh as much as Mount Everest. The collapse halts abruptly when the core reaches nuclear density, creating a shock wave that propagates outward through the star's outer layers. This shock wave, traveling at speeds of up to 30,000 kilometers per second, tears through the star's atmosphere, heating the stellar material to temperatures of billions of degrees and accelerating it to a significant fraction of the speed of light. The star's outer layers are blown away in a spectacular explosion that can briefly outshine an entire galaxy containing hundreds of billions of stars. The energy released in this explosion is almost incomprehensible. A typical supernova releases about 10 to the power of 44 joules of energy, equivalent to the total energy output of our sun over its entire lifetime, released in a matter of seconds. Most of this energy is carried away by neutrinos, nearly massless particles that interact so weakly with matter that they can pass through the entire Earth without being absorbed. The neutrinos from a supernova explosion carry away 99% of the explosion's energy, streaming out into space at nearly the speed of light. The Crab Nebula in the constellation Taurus provides us with a spectacular example of a supernova remnant. Chinese astronomers recorded the appearance of this guest star in 1054 CE, noting that it was visible during the day for 23 days and remained visible to the naked eye for nearly 2 years. Today, nearly 1,000 years later, we can observe the ongoing expansion of the debris from this explosion, forming a beautiful, complex nebula that continues to grow at a rate of about 1,500 kilometers per second. At the heart of the Crab Nebula lies the Crab Pulsar, a neutron star that rotates 30 times per second, sweeping beams of radiation across space like a cosmic lighthouse. This pulsar is one of the most precisely periodic objects known in the universe, maintaining its rotation rate with accuracy that rivals the best atomic clocks. The energy for this emission comes from the rotational energy of the neutron star itself, which gradually slows down as it loses energy through radiation. The Vela supernova remnant tells a similar story from our galaxy's more distant past. This explosion occurred approximately 11,000 years ago, relatively close to Earth, at a distance of only 815 light-years. The shock wave from this explosion is still expanding today, creating a bubble of hot gas that spans 8 degrees of sky, 16 times the diameter of the full moon. The Vela pulsar, spinning 11 times per second, continues to energize the surrounding nebula with its powerful magnetic field and particle wind. Supernovae serve as cosmic alchemists, creating and dispersing heavy elements throughout the galaxy. During the explosion, the extreme temperatures and pressures forge elements heavier than iron, gold, platinum, uranium, and dozens of other elements that cannot be created through normal stellar nucleosynthesis. These elements, ejected into space at tremendous speeds, eventually become incorporated into the interstellar medium, enriching the raw material from which future generations of stars and planets will form. The shock waves from supernovae also play a crucial role in triggering new episodes of star formation. As the expanding shell of hot gas encounters nearby molecular clouds, it compresses the gas and dust, creating the conditions necessary for gravitational collapse and the birth of new stars. In this way, stellar death becomes a catalyst for stellar birth, continuing the cycle of cosmic renewal that has shaped our galaxy for billions of years. Type Ia supernovae represent a different category of stellar explosion, occurring in binary star systems where a white dwarf star gradually accretes material from a companion star. When the white dwarf's mass approaches the Chandrasekhar limit, about 1.4 times the mass of our Sun, the star becomes unstable and explodes in a thermonuclear detonation that completely destroys the white dwarf. These explosions are remarkably uniform in their brightness, making them valuable, standard candles for measuring cosmic distances. The discovery that Type Ia supernovae appear dimmer than expected at great distances led to one of the most important cosmological discoveries of the 20th century: the accelerating expansion of the universe. This observation provided the first evidence for dark energy, the mysterious force that appears to be driving the universe's expansion to accelerate over time. Cassiopeia A represents one of the youngest known supernova remnants in our galaxy, with the explosion estimated to have occurred around 1680 CE. Despite its youth, this remnant has already expanded to a diameter of about 10 light-years, and it continues to provide valuable insights into the supernova process. The complex structure of Cassiopeia A, with its bright knots and filaments of glowing gas, reveals the three-dimensional nature of the explosion and the way the blast wave interacts with the surrounding interstellar medium. The Tycho supernova remnant, named after the Danish astronomer Tycho Brahe, who observed the explosion in 1572, demonstrates how supernovae can be visible from enormous distances. Brahe's supernova was bright enough to be seen during the day and remained visible to the naked eye for over a year. Modern observations reveal a beautiful, nearly spherical shell of expanding gas, heated to millions of degrees by the ongoing shockwave from the 450-year-old explosion. Some supernovae are so massive that even the neutron degeneracy pressure cannot halt the core collapse. In these cases, the collapsing core continues to shrink beyond the neutron star stage, forming a black hole. These hypernova explosions can be even more energetic than typical supernovae, and they may be associated with gamma-ray bursts, the most energetic explosions known in the universe. The study of supernovae has revealed that these explosions are not random events but follow predictable patterns based on stellar mass and evolutionary stage. Stars with masses between 8 and 25 times that of our Sun typically produce neutron stars, while more massive stars collapse to form black holes. Binary star systems can produce Type Ia explosions regardless of the primary star's initial mass, as long as one component evolves into a white dwarf and can accrete sufficient material from its companion. The enrichment of the galaxy through supernova explosions has profound implications for the development of planetary systems and the emergence of life. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were forged in the nuclear furnaces of massive stars and dispersed through space by supernova explosions. We are quite literally made of star stuff, carrying within us the legacy of stellar deaths that occurred billions of years ago. The neutron stars left behind by some supernovae represent some of the most extreme objects in the universe. With magnetic fields trillions of times stronger than Earth's, surface temperatures of millions of degrees, and gravitational fields so intense that the escape velocity approaches half the speed of light, neutron stars exist at the very limits of physics. Some neutron stars, known as magnetars, have magnetic fields so strong that they would be lethal to human life at distances of thousands of kilometers. Pulsar wind nebulae, created by the interaction between rapidly rotating neutron stars and their surrounding environment, produce some of the most beautiful and complex structures in the cosmos. The Crab nebulae's intricate filaments and knots result from the interaction between the pulsar's particle wind and the expanding supernova ejecta, creating a dynamic system that continues to evolve nearly 1,000 years after the original explosion. As we contemplate these cosmic catastrophes, we witness the universe's fundamental processes of creation and destruction, operating on scales that dwarf human comprehension. The violence of a supernova explosion, though capable of sterilizing entire solar systems, also serves as the universe's primary mechanism for creating and distributing the heavy elements essential for rocky planets and biological life. In the gentle expansion of ancient supernova remnants, we see the aftermath of stellar violence transformed into objects of ethereal beauty. The shock waves that once carried temperatures of billions of degrees now drive the slow, majestic expansion of glowing gas clouds that will continue to grow and fade over hundreds of thousands of years. Though violent, the end of a star is a quiet reverberation that lingers across time and space, enriching the cosmos with the elements of complexity and seeding the galaxy with the raw materials for future worlds. In death, these massive stars achieve a kind of immortality, their atoms becoming part of planets, moons, and perhaps even living beings in solar systems yet to be born. In the deepest reaches of space, where the very fabric of reality bends and warps under the influence of extreme gravity, there exist objects so massive and dense that nothing, not matter, not light, not even information itself, can escape their gravitational embrace once it crosses a certain boundary. These are the black holes, perhaps the most mysterious and fascinating objects in the universe, where our understanding of physics reaches its limits and the familiar laws of space and time break down in ways that challenge our most fundamental assumptions about reality. Black holes represent the ultimate victory of gravity over all other forces in nature. Born from the collapse of the most massive stars or through other exotic processes in the early universe, they are regions of space-time where gravity has become so strong that it warps the very geometry of space and time into an inescapable prison. Yet despite their reputation as cosmic vacuum cleaners, black holes are not the indiscriminate destroyers of science fiction. They are, instead, remarkably stable and predictable objects that follow precise mathematical laws and play crucial roles in shaping the large-scale structure of the universe. The concept of a black hole emerges naturally from Einstein's theory of general relativity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Just as a heavy ball placed on a stretched rubber sheet creates a depression that causes smaller objects to roll toward it, massive objects warp the fabric of space-time, creating gravitational fields that influence the motion of nearby matter and energy. In the case of a black hole, this warping becomes so extreme that it creates a region from which escape is impossible. The boundary of this inescapable region is called the event horizon, a spherical surface surrounding the black hole, beyond which no information can flow outward. The event horizon is not a physical surface like the boundary of a planet or star, but rather a mathematical construct that marks the point of no return. Its radius, known as the Schwarzschild radius, depends only on the mass of the black hole. The more massive the black hole, the larger its event horizon. For a black hole with the mass of our Sun, the event horizon would have a radius of approximately 3 kilometers. Earth, if compressed to form a black hole, would have an event horizon only 9 millimeters in radius, smaller than a marble. These comparisons help illustrate the extreme density required to create a black hole. Matter must be compressed far beyond the density of atomic nuclei, beyond even the density of neutron stars, to the point where the very structure of space and time breaks down. At the center of every black hole lies the singularity, a theoretical point where density becomes infinite and the curvature of space-time becomes infinitely steep. Here, our current understanding of physics breaks down completely. The singularity represents a fundamental limit to scientific knowledge, a place where the equations of general relativity produce mathematical infinities and lose their predictive power. Whether singularities actually exist in nature or whether some unknown physics intervenes to prevent their formation remains one of the deepest mysteries in theoretical physics. The supermassive black hole at the center of our galaxy, known as Sagittarius A, pronounced Sagittarius a star, provides a magnificent example of these cosmic behemoths in action. With a mass approximately 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury, Sagittarius A exerts a gravitational influence that can be observed in the orbital motions of nearby stars. Astronomers have tracked individual stars as they orbit this invisible giant, their elliptical paths providing direct evidence for the black hole's existence and allowing precise measurements of its mass. The environment around Sagittarius A is a dynamic and violent place. As matter falls toward the black hole, it forms an accretion disk, a swirling vortex of superheated gas and plasma that spirals inward at tremendous speeds. Friction within this disk heats the material to temperatures of millions of degrees, causing it to glow brilliantly across the electromagnetic spectrum. The inner edge of the accretion disk can extend to within just a few times the event horizon radius, where the orbital velocities approach significant fractions of the speed of light. The process of accretion onto a black hole is remarkably efficient at converting matter into energy. While nuclear fusion, the process that powers stars, converts about 0.7% of matter into energy, accretion onto a black hole can convert up to 42% of the infalling matter into radiant energy. This makes actively accreting black holes among the most luminous objects in the universe, capable of outshining entire galaxies despite being millions of times smaller. As matter spirals into a black hole, tidal forces, differences in gravitational pull across extended objects, become increasingly important. An astronaut falling feet first toward a stellar mass black hole would experience stronger gravitational pull on their feet than on their head, stretching them vertically while simultaneously compressing them horizontally. This process, whimsically known as spaghettification, would ultimately tear apart any extended object long before it reached the event horizon. However, for supermassive black holes like Sagittarius A, the tidal forces at the event horizon are much gentler. An astronaut could, in principle, cross the event horizon of a supermassive black hole without immediate harm, though they would never be able to communicate their experience to the outside universe. This difference in tidal forces between stellar mass and supermassive black holes illustrates how the physics of black holes depends critically on their mass and size. The study of black holes has revealed some of the most profound insights in modern physics. Stephen Hawking's discovery that black holes emit radiation due to quantum effects near the event horizon revolutionized our understanding of the relationship between gravity, quantum mechanics, and thermodynamics. Hawking radiation, as it came to be known, suggests that black holes are not perfectly black, but instead emit a faint thermal radiation that causes them to slowly evaporate over time. The temperature of Hawking radiation is inversely proportional to the black hole's mass. The more massive the black hole, the cooler its radiation. For stellar mass black holes, this radiation is incredibly faint, with temperatures of only a few billionths of a degree above absolute zero. For supermassive black holes, the temperature is even lower. At these temperatures, the rate of evaporation is so slow that it would take longer than the current age of the universe for even the smallest black holes to evaporate completely. Intermediate mass black holes, with masses between those of stellar mass and supermassive black holes, remain somewhat mysterious. While stellar mass black holes form from the collapse of massive stars, and supermassive black holes are thought to grow through accretion and mergers over billions of years, the formation mechanism for intermediate mass black holes is less clear. They may form through the direct collapse of very massive stars in the early universe, or through the gradual growth of smaller black holes in dense stellar environments. The recent detection of gravitational waves by the LIGO and Virgo collaborations has opened a new window into the study of black holes. These ripples in space-time itself are produced when two black holes spiral together and merge, releasing enormous amounts of energy in the form of gravitational radiation. The first detected gravitational wave event, GW 15914, involved the merger of two black holes with masses about 30 times that of the Sun, located over 1 billion light-years from Earth. Gravitational wave astronomy has revealed a previously unknown population of black holes, with masses larger than those typically formed by stellar collapse. These observations suggest that black holes can grow significantly through mergers, and that such mergers were more common in the early universe, when galaxies were smaller and more densely packed. Each merger event provides unique insights into the properties of black holes, and tests Einstein's predictions about gravity in the strongest gravitational fields that exist in nature. The supermassive black holes found at the centers of most large galaxies appear to be intimately connected to the evolution of their host galaxies. The mass of a central black hole correlates remarkably well with the mass of the galaxy's central bulge, suggesting that galaxies and their central black holes grew together through some kind of feedback process. When a supermassive black hole accretes matter actively, it can produce powerful jets of high-energy particles that extend for hundreds of thousands of light-years, influencing star formation throughout the entire galaxy. These active galactic nuclei, or AGNs, represent some of the most energetic phenomena in the universe. Quasars, the most luminous type of AGN, can outshine their entire host galaxies by factors of hundreds or thousands, making them visible across cosmic distances that span a significant fraction of the observable universe. The energy source for this tremendous luminosity is the gravitational potential energy of matter falling into the supermassive black hole, converted to radiation with remarkable efficiency. The event horizon of a black hole represents a boundary not just in space, but in the flow of information. According to general relativity, an outside observer would never actually see an object cross the event horizon. Instead, they would see it slow down and red shift as it approaches the boundary, its image fading and becoming redder until it disappears from view. This apparent contradiction between different perspectives, the infalling observer experiences crossing the event horizon normally, while the outside observer never sees it happen, highlights the relative nature of space and time near black holes. Black holes also exhibit a property known as no hair, meaning that they are characterized completely by just three quantities: mass, electric charge, and angular momentum, spin. All other information about the matter that formed the black hole is lost, leading to what is known as the information paradox. This apparent destruction of information conflicts with the principles of quantum mechanics, which require that information be conserved. Resolving this paradox remains one of the most important challenges in theoretical physics. Rotating black holes, described by the Kerr metric, exhibit additional fascinating properties. The rotation drags space-time around with it, creating a region called the ergosphere, where it becomes impossible to remain stationary relative to distant observers. Objects in the ergosphere are forced to rotate along with the black hole, though they can still escape if they have sufficient energy. This frame-dragging effect represents one of the most exotic predictions of general relativity, confirmed through observations of matter orbiting near rotating black holes. The study of black holes near the galactic center has provided some of the most stringent tests of general relativity in strong gravitational fields. The star S2, which orbits Sagittarius A with a period of 16 years, reaches speeds of up to 5,000 kilometers per second at its closest approach. Observations of this star's orbit have confirmed predictions of general relativity, including gravitational redshift and relativistic precession, providing direct evidence for Einstein's theory in the regime of strong gravity. Primordial black holes, if they exist, represent a different class of black holes that could have formed in the early universe through the direct collapse of density fluctuations, rather than through stellar evolution. These hypothetical objects could have a wide range of masses, from microscopic black holes to those more massive than the Sun. Some theories suggest that primordial black holes could account for some or all of the dark matter in the universe, though current observations place strict limits on their abundance. The imaging of black holes represents one of the greatest technological achievements in astronomy. The Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, has captured images of the shadows cast by supermassive black holes against their glowing accretion disks. These images provide direct visual evidence for the existence of event horizons and confirm many theoretical predictions about black hole physics. As we contemplate these cosmic behemoths, we encounter objects that challenge our intuitive understanding of space, time, and causality. Black holes represent the extremes of physics, where matter is compressed to infinite density, where time dilation becomes infinite, and where the very concept of inside and outside loses its usual meaning. Yet despite their exotic properties, black holes are governed by precise mathematical laws that make them predictable, and in their own way beautiful. In the gentle spiral of matter around a black hole's event horizon, we witness gravity's ultimate expression, not as a force of destruction, but as a sculptor of space-time itself. The accretion disks that surround these cosmic giants glow with the light of matter's final journey, creating some of the most luminous and beautiful objects in the universe from the process of gravitational collapse. A black hole is not just a void, it is the darkness at the heart of galaxies, where space and time bend and warp into configurations that reveal the deepest truths about the nature of reality itself. In their silent presence, we find not emptiness, but the profound mystery of existence, distilled to its most fundamental level, where the universe's strangest and most beautiful secrets lie hidden behind horizons that separate the known from the unknown. In the vast cosmic architecture that surrounds us, there exists a hidden framework, an invisible scaffolding that holds the universe together, yet remains utterly beyond our direct perception. This is dark matter, perhaps the most humbling discovery in modern cosmology, reminding us that the atoms and energy we can observe directly comprise only a small fraction of all that exists. Dark matter makes up approximately 27% of the universe's total mass energy, dwarfing the mere 5% that consists of ordinary matter, the protons, neutrons, and electrons that form stars, planets, and everything we can see. The story of dark matter begins not with sophisticated theoretical predictions, but with careful observations of the cosmos that revealed something fundamentally unexpected about the nature of gravity on galactic scales. In the 1930s, astronomer Fritz Zwicky was studying the motion of galaxies within the Coma cluster, a massive collection of thousands of galaxies bound together by their mutual gravitational attraction. When he calculated the total mass needed to hold this cluster together, based on the observed motions of its member galaxies, he discovered that there was far more mass present than could be accounted for by all the visible stars and gas. Zwicky's observations revealed what he termed missing mass, though we now understand that the mass isn't missing at all. It's simply invisible to our telescopes and instruments. The galaxies in the Coma cluster were moving too fast to be held together by the gravitational influence of their visible matter alone. Some additional, unseen mass had to be present to provide the extra gravitational binding needed to prevent the cluster from flying apart. This puzzling discovery remained largely ignored for decades, until astronomer Vera Rubin began studying the rotation curves of individual galaxies in the 1970s. Her meticulous observations revealed another profound mystery. Stars in the outer regions of spiral galaxies were moving much faster than they should have been, based on the gravitational influence of the visible matter in those galaxies. According to Newtonian physics, stars farther from a galaxy's center should orbit more slowly, just as the outer planets in our solar system take longer to complete their orbits than the inner planets. Instead, Rubin found that stars in the outer parts of galaxies maintained roughly constant orbital velocities, regardless of their distance from the galactic center. This flat rotation curve, as it came to be known, implied that galaxies are embedded within massive halos of invisible matter that extends far beyond the visible disk of stars and gas. The gravitational influence of this dark matter halo provides the additional force needed to keep the outer stars moving at their observed high speeds. The evidence for dark matter extends far beyond individual galaxies and galaxy clusters. Computer simulations of cosmic evolution, which attempt to model how the universe evolved from its early, nearly uniform state to the complex web of galaxies and galaxy clusters we observe today, only match observations when dark matter is included. Without dark matter, the universe would not have had enough gravitational pull to form the large-scale structures we see around us. In these simulations, dark matter serves as the universe's hidden architecture, providing the gravitational framework around which ordinary matter can condense and form stars and galaxies. Dark matter began clumping together under its own gravity very early in cosmic history, long before ordinary matter had cooled enough to form neutral atoms. These dark matter concentrations created the gravitational wells into which ordinary matter would later fall, seeding the formation of the first stars and galaxies. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, provides another crucial piece of evidence for dark matter's existence. Tiny temperature fluctuations in this ancient light reveal the pattern of density variations in the early universe, and the detailed characteristics of these fluctuations can only be explained if dark matter was already present when the universe was only 380,000 years old. The nature of dark matter remains one of the greatest mysteries in physics. We know it must interact gravitationally, since we can observe its gravitational effects on visible matter, but it appears to interact very weakly, if at all, with electromagnetic radiation. This means dark matter doesn't emit, absorb, or reflect light, making it effectively invisible to all our conventional astronomical instruments. It also seems to interact only weakly with ordinary matter through forces other than gravity, allowing it to pass through ordinary matter as if it weren't there. One of the leading candidates for dark matter particles is the WIMP, weakly interacting massive particle. These hypothetical particles would have masses tens or hundreds of times greater than a proton, but would interact with ordinary matter only through gravity and the weak nuclear force. If WIMPs exist, they would be streaming through our bodies and through the Earth at every moment, but their interactions would be so rare that detecting them requires incredibly sensitive instruments housed in deep underground laboratories, shielded from cosmic rays and other sources of background radiation. Despite decades of searching, dark matter particles have not yet been directly detected. Underground detectors filled with liquid xenon or other target materials wait patiently for the rare collision between a dark matter particle and an atomic nucleus that would provide direct evidence for these elusive particles. Other experiments attempt to create dark matter particles in high-gallery collider experiments, while still others search for the products of dark matter particle annihilation in space. Alternative theories, such as modified Newtonian dynamics, MOND, attempt to explain the observed phenomena without invoking invisible matter. These theories propose that our understanding of gravity itself may be incomplete, and that gravitational forces behave differently on galactic scales than they do in our solar system. While MOND can explain some galactic rotation curves, it struggles to account for the full range of observations that support the dark matter hypothesis, particularly the patterns observed in the cosmic microwave background and the behavior of galaxy clusters during collisions. The Bullet Cluster provides one of the most compelling pieces of evidence for the existence of dark matter as actual particles, rather than a modification of gravitational theory. This system consists of two galaxy clusters that collided and passed through each other millions of years ago. During the collision, the hot gas in each cluster interacted electromagnetically, and was slowed down, while the dark matter in each cluster, interacting only gravitationally, passed through largely unaffected. Gravitational lensing observations of the bullet cluster reveal that the majority of the mass in the system is located where the dark matter should be, separated from the hot gas that makes up most of the visible matter. This spatial separation between the visible matter and the gravitational mass provides strong evidence that dark matter consists of actual particles that can be gravitationally separated from ordinary matter during cosmic collisions. Gravitational lensing has become one of the most powerful tools for mapping the distribution of dark matter throughout the universe. When light from distant galaxies passes through regions of space containing dark matter concentrations, the dark matter's gravitational field bends the light's path, distorting the images of the background galaxies. By carefully analyzing these distortions, astronomers can create maps showing where dark matter is located, even though it remains completely invisible. These dark matter maps reveal a cosmic web of interconnected filaments stretching across hundreds of millions of light years, with galaxy clusters located at the intersections of these filaments. The distribution of dark matter follows a pattern predicted by computer simulations of cosmic evolution, providing additional confirmation that our understanding of dark matter's role in shaping the universe is fundamentally correct. The search for dark matter has driven the development of some of the most sensitive scientific instruments ever created. Underground detectors must be capable of distinguishing the tiny energy deposits from hypothetical dark matter collisions, from the much larger signals produced by cosmic rays, radioactive decay, and other background sources. These experiments push the boundaries of low external detection technology and quantum sensing technique. Direct detection experiments have gradually increased their sensitivity over the past several decades, ruling out many theoretical models for dark matter particles, while opening up new regions of parameter space for exploration. Each null result provides valuable information about what dark matter is not, helping to constrain theoretical models and guide the design of future experiments with even greater sensitivity. Indirect detection strategies search for the products of dark matter particle interactions in space. When dark matter particles collide and annihilate with each other, they should produce high-energy photons, neutrinos, or other particles that could be detected by space-based telescopes or ground-based detectors. Observations of the galactic center, dwarf spheroidal galaxies, and other dark matter-rich regions have placed stringent limits on the rate of such interactions. The Large Hadron Collider and other particle accelerators search for dark matter by attempting to create these particles in high-energy collisions between protons or other particles. If dark matter particles can be produced in collider experiments, they would immediately escape the detector without leaving a direct trace. But their presence could be inferred from missing energy and momentum in the collision products. Axions represent another class of dark matter candidates, extremely light particles that were originally proposed to solve a different problem in particle physics, but could also make up some or all of the dark matter. Axion detection experiments use powerful magnetic fields and sensitive microwave receivers to search for the tiny signals that would be produced if axions convert to photons in the presence of a magnetic field. The mystery of dark matter extends beyond its fundamental nature to questions about its distribution and behavior on smaller scales. Computer simulations predict that dark matter should form numerous small subhalos within larger galaxy halos, but observations have found fewer small satellite galaxies around the Milky Way than these simulations predict. This discrepancy, known as the missing satellite problem, may indicate that our understanding of dark matter physics is incomplete, or it may simply reflect the difficulty of forming stars in the smallest dark matter halos. Self-interacting dark matter models propose that dark matter particles can collide with each other through forces other than gravity, potentially solving some of the discrepancies between observations and simulations on galactic scales. These interactions could smooth out the central regions of dark matter halos, making them less dense than predicted by simulations that assume dark matter interacts only gravitationally. As we contemplate the invisible architecture of the cosmos, we confront a humbling reminder of how much remains unknown about the universe we inhabit. Dark matter surrounds us, flows through us, and shapes the cosmic environment that enables galaxies, stars, and planets to exist. Yet it remains as mysterious today as when it was first discovered nearly a century ago. In the gentle gravitational embrace of dark matter halos, galaxies rotate with stately grace, their spiral arms maintained by the invisible scaffolding that holds them together. The cosmic web of dark matter filaments guides the flow of ordinary matter through space, channeling gas and dust toward the intersections where new galaxies are born and clusters grow. Though unseen, dark matter holds the universe in place, its silent force holding galaxies together while allowing the cosmic expansion to carry them apart. In its invisible presence, we find both mystery and meaning. A reminder that the universe contains depths of complexity and beauty that extend far beyond what our eyes can see, challenging us to expand our understanding of what it means to exist within this vast, dark, and wonderful cosmos. Deep within the cosmos, hidden behind the dense stellar fields and obscuring dust clouds of our own Milky Way galaxy, lies one of the most enigmatic structures in the known universe. The Great Attractor, as astronomers have named it, is a gravitational anomaly of staggering proportions. A concentration of mass so immense that it exerts its influence across hundreds of millions of light years, pulling entire galaxy clusters toward it in a cosmic dance that has been unfolding for billions of years. The discovery of the Great Attractor emerged from careful observations of the cosmic microwave background radiation and the peculiar motions of galaxies in our local cosmic neighborhood. In the 1970s and 1980s, astronomers began to notice that our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, was not moving randomly through space as might be expected in a uniformly expanding universe. Instead, our entire local region appeared to be drifting in a specific direction at a velocity of approximately 600 kilometers per second. This peculiar motion, known as the dipole anisotropy in the cosmic microwave background, revealed itself as a slight temperature difference in the ancient radiation that fills all of space. The direction toward which we are moving appears slightly warmer due to the Doppler effect, while the opposite direction appears slightly cooler. This observation provided the first hint that something massive and distant was exerting a gravitational influence strong enough to affect the motion of our entire local region of the universe. The Great Attractor lies approximately 250 million light-years away in the direction of the constellations Hydra and Centaurus, unfortunately positioned almost directly behind the plane of our own galaxy. This location places it in what astronomers call the zone of avoidance, a region of sky where the dense concentration of stars, gas, and dust in the Milky Way's disk makes it extremely difficult to observe distant objects. The cosmic irony is profound. One of the most significant gravitational influences on our local cosmic environment remains largely hidden from our direct view. Despite these observational challenges, astronomers have gradually pieced together a picture of the Great Attractor through multiple lines of evidence. Radio astronomy, which can penetrate the obscuring material in our galaxy's disk, has revealed the presence of numerous galaxy clusters in the general direction of the Great Attractor. Infrared observations, less affected by dust absorption than visible light, have also provided glimpses of the massive structures hidden behind the Milky Way. The gravitational influence of the Great Attractor extends far beyond its immediate vicinity. Galaxy redshift surveys have shown that thousands of galaxies across a vast region of space are all flowing toward this mysterious concentration of mass. This motion is superimposed on the general expansion of the universe, creating a pattern of peculiar velocities that reveals the underlying distribution of matter on cosmic scales. One of the most significant components of the Great Attractor region is the Norma cluster, a massive galaxy cluster that lies partially hidden behind the Milky Way. This cluster, also known as Abell 3627, contains hundreds of galaxies bound together by their mutual gravitational attraction. X-ray observations have revealed hot gas filling the space between the cluster's member galaxies, heated to temperatures of tens of millions of degrees by the gravitational potential well of the cluster. The Centaurus cluster represents another major component of the Great Attractor region. Located slightly closer to Earth at a distance of about 170 million light-years, This cluster is one of the largest and most massive galaxy clusters in the nearby universe. The cluster's central region is dominated by the giant elliptical galaxy, NGC 5128, also known as Centaurus A, which shows clear signs of recent galactic merger activity and harbors an active supermassive black hole at its center. However, even when astronomers account for all the known galaxy clusters and individual galaxies in the Great Attractor region, the total observed mass falls short of what would be needed to explain the strength of the gravitational pull being exerted on our local cosmic neighborhood. This mass deficit suggests that the Great Attractor's influence may be due not to a single, localized concentration of matter, but rather to a more extended distribution of mass that includes significant amounts of dark matter. Recent large-scale galaxy surveys have revealed that the Great Attractor may be part of an even larger structure known as the Laniakea supercluster. This immense cosmic architecture spans more than 500 million light-years and contains the mass equivalent of approximately 100,000 trillion suns. Within this vast structure, the Milky Way and millions of other galaxies are all flowing along streamlines of gravitational influence that converge toward a central region called the Great Attractor. The discovery of Laniakea has fundamentally changed our understanding of our place in the cosmic hierarchy. Just as we learned that Earth orbits the Sun, that the Sun orbits within the Milky Way galaxy, and that the Milky Way is part of the local group of galaxies, we now understand that our local group is itself part of a much larger gravitationally bound structure that encompasses thousands of galaxy groups and clusters. The motion of galaxies toward the Great Attractor is not a simple, uniform flow, but rather a complex pattern of streaming motions that reveal the three-dimensional structure of matter distribution in the local universe. Computer simulations of cosmic structure formation predict that such large-scale flows should exist, driven by the gravitational influence of the most massive concentrations of dark matter. The observed peculiar velocities match these theoretical predictions remarkably well, providing strong support for our understanding of how cosmic structures grow and evolve over time. The study of the Great Attractor and similar large-scale structures has profound implications for our understanding of cosmology and the ultimate fate of the universe. These massive concentrations of matter represent regions where the cosmic expansion has been halted or even reversed on local scales, creating bound systems that will continue to grow through gravitational accretion even as the universe as a whole continues to expand and cool. Within the gravitational sphere of influence of the Great Attractor, the familiar pattern of cosmic expansion gives way to more complex dynamics. Galaxies and galaxy clusters that would otherwise be carried apart by the expansion of space instead flow toward the massive concentration of matter, their paths curved by the same gravitational forces that shape the large-scale structure of the universe over billions of years. The zone of avoidance continues to present significant challenges for astronomers studying the Great Attractor region. Advanced observational techniques, including radio astronomy and near-infrared surveys, are gradually revealing more details about the hidden structures behind the Milky Way. Future space missions and ground-based observatories will continue to probe this mysterious region, potentially discovering additional massive structures that contribute to the Great Attractor's gravitational influence. One of the most intriguing aspects of the Great Attractor is its relationship to even larger cosmic structures. Beyond Laniakea lies the Shapley supercluster, an even more massive concentration of galaxy clusters that may be responsible for additional peculiar motions observed in our local cosmic neighborhood. These nested hierarchies of structure suggest that the universe contains organizational patterns on scales that challenge our intuitive understanding of cosmic architecture. The Great Attractor also plays a role in shaping the local void, a vast region of space with unusually low galaxy density that lies in the opposite direction from the Great Attractor. This cosmic void, stretching across hundreds of millions of light-years, may have been emptied of matter through the same gravitational processes that concentrated mass in the Great Attractor region. The interplay between cosmic voids and over-dense regions like the Great Attractor creates the web-like pattern of matter distribution that characterizes the large-scale structure of the universe. Gravitational wave astronomy may eventually provide new insights into the Great Attractor region. As gravitational wave detectors become more sensitive, they may be able to detect the signals from black hole mergers and neutron star collisions occurring within the massive galaxy clusters that comprise the Great Attractor. These observations could reveal details about the mass distribution and dynamics of these hidden structures that remain difficult to study through electromagnetic radiation alone. The mysterious nature of the Great Attractor extends to questions about its ultimate origin and evolution. Computer simulations suggest that such massive structures form through the hierarchical merging of smaller galaxy groups and clusters over cosmic time. The Great Attractor region may represent an ongoing collision between multiple massive structures, creating a dynamic and evolving gravitational landscape that will continue to change over billions of years. Dark energy, the mysterious force driving the accelerated expansion of the universe, also influences the dynamics of the Great Attractor region. While gravity works to pull matter together into bound structures, dark energy acts to accelerate the expansion of space itself, competing with gravitational collapse on the largest scales. The balance between these opposing forces determines which structures will continue to grow and which will be torn apart by cosmic expansion. The study of peculiar velocities in the Great Attractor region has also provided insights into the nature of dark matter on cosmic scales. The observed patterns of galaxy motions match theoretical predictions for how dark matter should behave under the influence of gravity, supporting models in which dark matter consists of particles that interact primarily through gravitational forces. Future astronomical surveys will continue to map the three-dimensional distribution of galaxies around the Great Attractor, gradually building a more complete picture of this cosmic leviathan. The Vera C. Rubin Observatory, with its ability to survey the entire visible sky repeatedly, will discover millions of new galaxies and provide unprecedented detail about the large-scale structure of the nearby universe. As we contemplate this vast cosmic attractor, we encounter the universe operating on scales that dwarf even the most massive individual objects. The Great Attractor represents gravity working not on the scale of stars or even galaxies, but on the scale of cosmic architecture itself, shaping the flow of matter across hundreds of millions of light years and influencing the motions of structures containing trillions of stars. In the patient persistence of this cosmic pull, we witness the universe's tendency toward organization and structure, the same fundamental processes that allowed matter to clump together and form the first stars and galaxies in the early universe. The Great Attractor continues this ancient work of cosmic construction, slowly drawing together the raw materials for future galactic collisions and mergers that will reshape the local universe over billions of years to come. A force, unseen but felt across vast distances, tugging at the fabric of space itself, reminding us that even in the apparent emptiness between galaxies, the universe remains connected through invisible threads of gravitational influence that bind the cosmos together in an intricate web of matter, energy, and space-time that continues to evolve and grow throughout the vast expanses of cosmic time. In the deepest reaches of observable space, where galaxies appear as mere points of light and the universe reveals its most ancient secrets, there shine beacons of such extraordinary brilliance that they can outshine entire galaxies containing hundreds of billions of stars. These are the quasars, quasi-stellar radio sources, among the most luminous and energetic phenomena in the cosmos, powered by processes so extreme that they challenge our understanding of the physical limits of nature itself. When astronomers first discovered quasars in the 1960s, they appeared as mysterious point sources of radio emission that looked like individual stars in optical telescopes. However, spectroscopic analysis revealed that these star-like objects were actually located at cosmological distances, billions of light years away, making them far more luminous than anything previously known. The realization that objects appearing as mere points of light could be visible across such vast cosmic distances implied energy outputs that seemed almost impossible to explain within the known laws of physics. The mystery deepened when astronomers observed rapid variations in quasar brightness, with some quasars changing their luminosity significantly over periods of days or weeks. Since light travels at a finite speed, any astronomical object can only vary as quickly as light can travel across its size. For a quasar to vary in brightness over a period of days, its energy-producing region could be no larger than a few light days across, smaller than our solar system, yet somehow producing more energy than 1,000 galaxies. The solution to the quasar puzzle came with the understanding that these extraordinary objects are powered by supermassive black holes at the centers of distant galaxies, actively accreting matter from their surroundings. As material spirals into the black hole, it forms an accretion disk where gravitational energy is converted to thermal energy with remarkable efficiency. The intense friction within this disk heats the material to temperatures of millions of degrees, causing it to glow brilliantly across the entire electromagnetic spectrum. The central engines of quasars represent some of the most efficient energy conversion processes known in the universe. While nuclear fusion in stars converts only about 0.7% of matter into energy, the accretion process around a supermassive black hole can convert up to 42% of the infalling matter into radiant energy. This extraordinary efficiency allows a relatively small amount of material, perhaps just a few solar masses per year, to power the enormous luminosity of a quasar. The supermassive black holes that drive quasars contain millions to billions of times the mass of our Sun, compressed into regions smaller than our solar system. The event horizons of these cosmic giants can span distances comparable to the orbit of Neptune, yet the energy-producing accretion disk extends only a few times farther. Within this compact region, matter reaches velocities approaching significant fractions of the speed of light, creating conditions of temperature and density that exist nowhere else in the present-day universe. Many quasars exhibit powerful jets of high-energy particles that stream outward from the vicinity of the central black hole at velocities very close to the speed of light. These relativistic jets, collimated by strong magnetic fields, can extend for hundreds of thousands of light-years beyond the host galaxy, carrying enormous amounts of energy and momentum into the surrounding intergalactic medium. The formation and acceleration of these jets remains one of the most challenging problems in astrophysics, involving complex interactions between the black hole's spin, magnetic fields, and the accretion disk. The jets from powerful quasars create some of the most spectacular structures in the universe. When these high-energy particle beams collide with the tenuous gas of the intergalactic medium, they create vast lobes of synchrotron radiation that glow brightly at radio wavelengths. These radio lobes can span millions of light-years, making them among the largest individual structures in the known universe, single objects that dwarf entire galaxy clusters in their extent. Quasar 3 C273, the first quasar to be identified and studied in detail, remains one of the brightest and most famous examples of these cosmic lighthouses. Located approximately 2.4 billion light-years from Earth, 3 C273 shines with the luminosity of 4 trillion suns, making it easily visible through modest telescopes, despite its enormous distance. The jet extending from 3 C273 stretches for over 100,000 light-years and shows clear evidence of superluminal motion, apparent faster-than-light movement that results from the relativistic speeds of the jet material and its orientation nearly along our line of sight. The study of quasars has provided crucial insights into the early evolution of galaxies and the growth of supermassive black holes. Since we observe quasars as they existed billions of years ago due to the finite speed of light, they offer a window into cosmic conditions when the universe was much younger and more active. The most distant quasars, observed when the universe was less than 1 billion years old, reveal that supermassive black holes containing billions of solar masses existed surprisingly early in cosmic history. This early existence of massive black holes presents a significant challenge for our understanding of black hole formation and growth. To reach such enormous masses so early in cosmic history, these black holes must have either formed from very massive seeds in the primordial universe, or grown through accretion at rates near the theoretical maximum. The Eddington limit sets an upper bound on how quickly a black hole can accrete matter, based on the balance between gravitational attraction and radiation pressure from the luminous accretion disk. The relationship between quasars and their host galaxies reveals important connections between supermassive black hole growth and galaxy evolution. Modern observations have shown that the mass of a galaxy's central black hole correlates strongly with the mass of the galaxy's central bulge, suggesting that black holes and galaxies co-evolve through feedback processes. When a quasar is active, its enormous energy output can drive powerful galactic winds that either trigger or suppress star formation throughout the host galaxy. Gravitational lensing by intervening galaxies or galaxy clusters can create multiple images of distant quasars, providing natural telescopes that magnify and brighten these already luminous objects. Some gravitationally lensed quasars appear as multiple point sources in a characteristic pattern around the lensing galaxy, while others form spectacular Einstein rings when the alignment is nearly perfect. These lensed quasars serve as powerful probes of both the mass distribution of the lensing objects and the structure of the distant quasar itself. The variability of quasars extends across all wavelengths of electromagnetic radiation and timescales from hours to years. Rapid variations provide information about the size and structure of the accretion disk, while longer-term changes may reflect variations in the rate of matter falling into the black hole or changes in the orientation of relativistic jets. Some quasars undergo dramatic outbursts that increase their brightness by factors of hundreds or thousands, possibly due to the tidal disruption of stars that venture too close to the central black hole. Blazars represent a special class of quasars whose relativistic jets point nearly directly toward Earth. The relativistic beaming effect causes these objects to appear extraordinarily bright and variable, with some blazars changing their brightness by large factors over periods of hours. The radiation from blazars is dominated by non-thermal processes, creating broad, featureless spectra that extend from radio waves to gamma rays. The most distant quasars serve as cosmic probes of the intergalactic medium during the epoch of reionization, when the first stars and galaxies ionized the neutral hydrogen that filled space in the early universe. Observations of quasar spectra can reveal the properties of intervening gas clouds through absorption line systems, providing detailed information about the chemical composition and physical conditions of matter along the line of sight. Modern surveys have discovered hundreds of thousands of quasars across the observable universe, revealing the cosmic evolution of supermassive black hole activity over billions of years. The quasar population was most active when the universe was roughly 2 to 3 billion years old, corresponding to a period of rapid galaxy formation and merging. This quasar epoch represents a time when supermassive black holes were growing most rapidly, fed by abundant supplies of gas and smaller galaxies. The decline in quasar activity over cosmic time reflects the gradual exhaustion of gas supplies in galaxy centers and the growth of galaxies to sizes where they can retain their gas against quasar-driven winds. Most nearby galaxies harbor supermassive black holes at their centers, but these objects are now relatively quiescent, accreting matter at much lower rates than their distant ancient counterparts. Radio-quiet quasars, which lack powerful radio jets, represent the majority of the quasar population and may be powered by different accretion mechanisms than their radio-loud cousins. The dichotomy between radio-loud and radio-quiet quasars may reflect differences in black hole spin, magnetic field strength, or the properties of the surrounding accretion flow. The study of quasar-host galaxies requires sophisticated observational techniques to separate the bright point source of the quasar from the much fainter extended emission of the host galaxy. Advanced adaptive optics systems and space-based observations have revealed that quasars reside in galaxies spanning the full range of morphological types, from spiral galaxies to massive ellipticals, though the most luminous quasars tend to be hosted by the most massive galaxies. Quasar feedback plays a crucial role in regulating star formation and black hole growth in massive galaxies. The energy and momentum deposited by quasar winds and jets can heat and expel gas from the host galaxy, temporarily shutting down both star formation and black hole accretion. This self-regulating mechanism may explain why the most massive galaxies are typically red and dead, containing old stellar populations and little ongoing star formation. As we contemplate these cosmic beacons shining across billions of light years, we witness the universe at its most energetic and dynamic. Quasars represent the intersection of the largest and smallest scales in astrophysics. Supermassive black holes, no larger than our solar system, powering phenomena that influence entire galaxies and the space between them. In their brilliant luminosity, we see the universe during its most active phase, when galaxies were young and actively forming stars, when supermassive black holes were growing rapidly, and when the cosmic web of large-scale structure was still taking shape. The light we observe from the most distant quasars began its journey when the universe was a fraction of its current age, carrying information about cosmic conditions that no longer exist in the nearby universe. A quasar's light is the universe's brightest cry, but it echoes from the farthest reaches of time and space, a testament to the extraordinary forces that shaped the cosmos during its youth and continue to influence its evolution today. In their distant brilliance, these cosmic lighthouses remind us that the universe was once a far more violent and energetic place. Yet from this apparent chaos emerged the ordered structures of galaxies, stars, and planetary systems that provide the stage for our own existence. In the vast darkness between star systems, where the light of distant suns fades to mere points, and the cold of space reaches temperatures barely above absolute zero, there drift worlds that know no sunrise. These are the rogue planets, wanderers of the cosmic deep that have been cast out from their birth systems or formed in isolation, condemned to journey through the galaxy's empty spaces without the warmth and light of a parent star. The discovery of rogue planets represents one of astronomy's most recent and surprising revelations. For centuries, our understanding of planetary formation assumed that all worlds must orbit stars, bound by gravity to the nuclear furnaces that provide energy and stability to planetary systems. The realization that planets can exist in the interstellar void, traveling alone through the darkness, fundamentally challenges our conception of what constitutes a planetary system and expands the possible environments where worlds might exist. Current estimates suggest that rogue planets may outnumber the stars themselves in our galaxy. Gravitational microlensing surveys, which detect the brief brightening of background stars when massive objects pass in front of them, have revealed a population of free-floating, planetary mass objects that dwarfs the known population of planets orbiting stars. These observations suggest that our galaxy may contain billions or even trillions of rogue planets, making them among the most common types of worlds in the cosmos. The origins of rogue planets are as diverse as the cosmic environments in which they form. Many began their existence as ordinary planets within stellar systems, orbiting their parent stars for millions or billions of years before violent gravitational interactions ejected them into interstellar space. These ejection events can occur during the early stages of planetary system formation, when multiple massive planets migrate through their birth systems and gravitationally scatter smaller worlds into eccentric orbits that eventually carry them beyond the reach of their star's gravity. Close encounters between star systems can also liberate planets from their stellar bonds. When two stars pass near each other, their gravitational influence can disrupt the orbits of planets in both systems, sending some worlds careening into interstellar space. Binary star systems, where two stars orbit each other, create particularly complex gravitational environments, where planetary orbits can become unstable over long timescales, eventually resulting in planetary ejection. Other rogue planets may form through entirely different processes that bypass the traditional model of planet formation within stellar systems. In the dense environments of star-forming regions, gravitational collapse can create planetary mass objects directly from interstellar gas and dust, without requiring a parent star. These sub-brown dwarf objects, sometimes called planamos, blur the distinction between planets and failed stars, representing a continuum of low-mass objects that formed through gravitational collapse rather than accretion within a circumstellar disk. The environments that rogue planets experience during their interstellar journeys are unlike anything found in traditional planetary systems. Temperatures on rogue planets are determined primarily by internal heat sources rather than stellar radiation. For massive planets with substantial atmospheres, the greenhouse effect and radioactive decay can maintain subsurface temperatures warm enough to support liquid water, even in the absence of stellar heating. Jupiter-mass rogue planets may retain thick hydrogen atmospheres that provide insulation against the cold of space. Computer simulations suggest that such worlds could maintain subsurface oceans for billions of years, heated by the decay of radioactive elements in their rocky cores and the slow gravitational compression of their massive atmospheres. These hidden oceans, shielded from the harsh radiation environment of interstellar space, might provide stable environments where life could potentially evolve and persist. Smaller rogue planets face greater challenges in maintaining habitable conditions. Earth-sized worlds ejected into interstellar space would quickly lose their atmospheres to the cold and vacuum of space, becoming frozen, airless bodies. However, even these worlds might retain subsurface liquid water in underground aquifers, heated by radioactive decay and protected from freezing by layers of insulating rock and ice. The search for rogue planets requires innovative observational techniques, as these worlds emit no light of their own and are not illuminated by nearby stars. Gravitational microlensing has emerged as the primary method for detecting free-Liga planets, taking advantage of the fact that any massive object can bend light through its gravitational field. When a rogue planet passes between Earth and a background star, it creates a brief magnification of the star's light that can be detected by sensitive surveys monitoring millions of stars simultaneously. The Kepler Space Telescope, during its extended K2 mission, attempted to detect rogue planets through direct infrared emission. Young rogue planets, ejected from their birth systems within the past few million years, should still retain heat from their formation and be detectable as faint infrared sources moving against the background of more distant stars. While these surveys have not yet definitively detected rogue planets through direct emission, they have placed important constraints on the population of warm, recently ejected worlds. Wide-field infrared surveys such as the Wide-Field Infrared Survey Explorer and the upcoming Nancy Grace Roman Space Telescope are expected to discover numerous rogue planets through their thermal emission. These missions will be particularly sensitive to massive rogue planets that retain significant internal heat, potentially revealing a population of wandering gas giants throughout the galaxy. The nearest rogue planet to Earth may lie closer than the nearest star system. Given the estimated abundance of these worlds, statistical calculations suggest that rogue planets should exist within just a few light years of our solar system. However, detecting such nearby objects remains extremely challenging, as they would appear as faint, slowly moving points of infrared light against the much brighter background of the zodiacal dust cloud that fills our solar system. Some rogue planets may not travel alone through interstellar space. Binary planet systems, where two worlds orbit each other without a central star, could form during the ejection process if two planets are scattered together from their birth system. Wide binary planets, separated by distances comparable to the Earth-Moon system or larger, might maintain their gravitational bond while traveling through the galaxy as a pair. Rogue planets with moons present particularly intriguing possibilities for maintaining habitable environments. Tidal heating from a large moon could provide an additional energy source to supplement radioactive decay, potentially maintaining liquid water oceans for extended periods. The Jupiter system, with its tidally heated moons Europa, Enceladus, and others, demonstrates how moon-planet interactions can create habitable environments even in the absence of significant stellar heating. The detection of exomoons around rogue planets represents one of the greatest challenges in observational astronomy. These systems would be extremely faint and difficult to resolve, requiring space-based telescopes with unprecedented sensitivity and stability. However, the discovery of moon systems around rogue planets would provide crucial insights into the formation and evolution of planetary systems during their most chaotic phases. Rogue planets may also capture smaller objects during their interstellar journeys. As these worlds pass through the galaxy, they could gravitationally capture asteroids, comets, or even smaller rogue planets, gradually building up retinues of orbiting objects. Over billions of years, a rogue planet might assemble a complex system of captured bodies, creating a miniature planetary system centered on a world that never knew the light of a star. The atmospheres of rogue planets offer unique laboratories for studying atmospheric dynamics in extreme environments. Without stellar heating to drive atmospheric circulation, weather patterns on rogue planets would be powered primarily by internal heat sources and the planet's rotation. These conditions might produce atmospheric phenomena unlike anything observed in traditional planetary systems. Thick atmospheres on massive rogue planets could trap enough internal heat to maintain surface temperatures above the freezing point of water, despite the absence of stellar radiation. Hydrogen atmospheres on Super-Earth and Neptune-sized rogue planets might create powerful greenhouse effects, potentially maintaining temperate surface conditions for billions of years after ejection from their birth systems. The study of rogue planets also provides insights into the violent dynamics of planetary system formation and evolution. The ejection rates inferred from microlensing surveys suggest that most planetary systems experience significant gravitational instabilities during their early evolution, scattering a substantial fraction of their planetary populations into interstellar space. This process may be a natural consequence of planet formation, indicating that stable planetary systems like our own solar system may be relatively uncommon outcomes of the planet formation process. Computer simulations of planetary system evolution consistently produce populations of ejected planets with properties similar to those inferred from observational surveys. These models suggest that the early phases of planetary system evolution are characterized by chaotic gravitational interactions that reshape the architecture of planetary systems and scatter many worlds into interstellar space. The survivors of this process, planets that remain bound to their stars, represent a subset of worlds that happened to avoid ejection during the turbulent early history of their systems. The galactic population of rogue planets represents a vast reservoir of worlds that have experienced radically different evolutionary histories from planets that remained bound to stars. These worlds may preserve records of the early conditions in planetary systems, frozen in time during their ejection events. Studying rogue planets could provide unique insights into the composition and structure of planetary systems during their formation phases. Future space missions dedicated to rogue planet detection and characterization will revolutionize our understanding of these mysterious worlds. The Nancy Grace Roman Space Telescope will conduct the most sensitive search for rogue planets ever attempted, potentially discovering thousands of free-leafing worlds throughout the galaxy. Ground-based surveys using next-generation telescopes will complement these space-based observations, providing detailed follow-up studies of the most interesting rogue planet candidates. The possibility of life on rogue planets expands our conception of habitable environments far beyond the traditional habitable zones around stars. If life can evolve and persist in the subsurface oceans of rogue planets, it would suggest that biological processes are possible in environments that are completely disconnected from stellar energy sources. Such life would depend entirely on geochemical and geothermal energy sources, representing a form of biology that could persist throughout the galaxy, regardless of stellar conditions. As we contemplate these solitary worlds drifting through the cosmic dark, we encounter a population of planets whose existence challenges our fundamental assumptions about planetary systems and the environments where worlds can exist. Rogue planets remind us that the galaxy is filled with objects that exist in the spaces between the familiar landmarks of stars and stellar systems. In their silent journey through the interstellar void, rogue planets carry with them the stories of the violent gravitational interactions that shaped the early evolution of planetary systems throughout the galaxy. They are the scattered remnants of cosmic upheavals, worlds that have survived ejection from their birth systems to begin new chapters of existence in the darkness between stars. These rogue worlds wander in the void, free of the light we know, yet still moving through space, as testament to the dynamic and sometimes violent processes that govern planetary system evolution. In their lonely travels, they remind us that the universe contains multitudes of worlds, whose stories unfold far from the warming light of stars, in the vast and mysterious darkness that fills the spaces between solar systems. In the most profound depths of cosmic space, where the fabric of reality itself becomes the canvas for nature's grandest phenomena, there travel waves of such subtlety and elegance that they remained hidden from human detection for over a century after their theoretical prediction. These are gravitational waves, ripples in the very geometry of space-time that carry information about the most violent and energetic events in the universe, propagating across billions of light years at the speed of light to whisper their ancient stories to sensitive detectors on Earth. The concept of gravitational waves emerged from Albert Einstein's general theory of relativity, published in 1915, which revolutionized our understanding of gravity by describing it not as a force, but as the curvature of space-time caused by mass and energy. Einstein's field equations predicted that accelerating masses should create disturbances in this space-time curvature that propagate outward, like ripples on a pond, carrying energy away from their source and subtly stretching and compressing space itself as they pass. For decades, gravitational waves remained purely theoretical predictions, mathematical consequences of Einstein's equations that seemed impossible to detect directly. The effects of these space-time ripples are extraordinarily small. Even the most powerful gravitational wave sources produce distortions in space that amount to less than 1/10,000th the width of a proton over distances of several kilometers. This incredible sensitivity requirement pushed the boundaries of experimental physics to their absolute limits. The first indirect evidence for gravitational waves came from observations of the Hulse-Taylor binary pulsar system, discovered in 1974. This remarkable system consists of two neutron stars orbiting each other, with a period of just under 8 hours, with one neutron star spinning rapidly as a pulsar, emitting regular radio pulses that serve as a cosmic clock of extraordinary precision. Over decades of careful observation, astronomers Russell Hulse and Joseph Taylor measured a gradual decrease in the orbital period that matched exactly the energy loss predicted by general relativity through gravitational wave emission. The Hulse-Taylor pulsar provided compelling proof that gravitational waves exist and carry energy away from accelerating masses. But direct detection remained elusive until the construction of laser interferometer gravitational wave observatories. These remarkable instruments use laser light to measure tiny changes in the distance between widely separated test masses, achieving sensitivities that can detect relative length changes smaller than 1 part in 10 to the 21st power. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, consists of 2 identical detectors located in Louisiana and Washington state, each featuring 4-kilometer-long arms arranged in an L shape. When a gravitational wave passes through the detector, it alternately stretches space in one direction while compressing it in the perpendicular direction, causing tiny changes in the time it takes laser light to travel between mirrors at the ends of each arm. On September 14, 2015, at 14 hours 50 minutes 45 seconds, Coordinated Universal Time, both LIGO detectors simultaneously registered a characteristic chirp signal, lasting only 0.2 of a second. This signal, designated GW1 50914, marked humanity's first direct detection of gravitational waves, and opened an entirely new window onto the cosmos. The source of this historic detection was the collision and merger of 2 black holes, each roughly 30 times the mass of our Sun, located over 1 billion light-years from Earth. The black hole merger that produced GW1 50914 released more energy in gravitational waves during its final fraction of a second than all the stars in the observable universe emit in light. This staggering energy output, equivalent to the conversion of 3 solar masses entirely into gravitational radiation, demonstrates the incredible violence and power of cosmic events that remain completely invisible to traditional astronomical observations. The detection of gravitational waves confirmed Einstein's century-old prediction with remarkable precision, validating general relativity in the regime of strong gravitational fields and high velocities, where it had never been tested before. The observed waveform matched theoretical predictions with extraordinary accuracy, providing detailed information about the masses, spins, and orbital characteristics of the merging black holes. Following this groundbreaking detection, LIGO and its European counterpart Virgo have discovered dozens of gravitational wave events, revealing a previously hidden population of merging black holes and neutron stars throughout the universe. Each detection provides unique insights into the properties of these extreme objects and the cosmic environments where they form and evolve. The merger of 2 neutron stars, detected on August 17, 2017, and designated GW1 70817, marked another revolutionary moment in gravitational wave astronomy. Unlike black hole mergers, which produce only gravitational waves, neutron star mergers create electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. This multi-messenger observation, combining gravitational waves with traditional electromagnetic astronomy, provided unprecedented insights into the physics of matter at nuclear densities and confirmed that neutron star mergers are responsible for producing many of the heaviest elements in the universe. the electromagnetic counterpart to GW 170817, observed by dozens of telescopes around the world and in space, revealed the characteristic signature of a kilonova, a radioactive glow powered by the decay of newly synthesized heavy elements. Spectroscopic analysis of this afterglow confirmed the production of gold, platinum, and other rare elements, solving the long-standing mystery of where these precious metals originate in the cosmos. Gravitational waves carry information about their sources in ways that electromagnetic radiation cannot. While light can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through virtually everything unchanged, providing a clear view of events that might be completely hidden from conventional telescopes. This transparency allows gravitational wave detectors to probe the interiors of cosmic catastrophes and observe phenomena that are invisible to electromagnetic astronomy. The frequency evolution of gravitational waves from merging compact objects tells the story of the final moments before collision. As two black holes or neutron stars spiral together, they orbit faster and faster, producing gravitational waves of increasing frequency and amplitude. This characteristic chirp pattern, first heard in GW 150914, provides precise measurements of the object's masses and allows astronomers to determine their distance through the strength of the detected signal. Advanced detector networks, including LIGO, Virgo, and the Japanese Kagra Observatory, work together to triangulate the positions of gravitational wave sources on the sky. When multiple detectors observe the same event, the slight differences in arrival time at each location allow astronomers to determine the source direction, enabling follow-up observations with electromagnetic telescopes to search for optical, X-ray, and radio counterparts. The sensitivity of current gravitational wave detectors continues to improve through technological advances and infrastructure upgrades. Enhanced laser power, better vibration isolation, and improved mirror suspensions have gradually increased the volume of space that can be monitored for gravitational wave events. Each factor of 2 improvement in sensitivity corresponds to an 8-fold increase in the detectable volume, dramatically expanding the rate of observed mergers. Future gravitational wave observatories will extend humanity's reach even further into the cosmos. Third-generation ground-based detectors, such as the proposed Cosmic Explorer and Einstein telescope, will be 10 times more sensitive than current facilities, enabling the detection of black hole and neutron star mergers throughout the observable universe. These future instruments will observe hundreds of thousands of merger events per year, transforming gravitational wave astronomy from the study of individual events to statistical analysis of cosmic populations. Space-based gravitational wave detectors, led by the Laser Interferometer Space Antenna mission, planned for the 2030s, will open entirely new frequency ranges for gravitational wave astronomy. Operating in the vacuum of space, with arm lengths of millions of kilometers, these detectors will be sensitive to gravitational waves from supermassive black hole mergers, galactic binary star systems, and possibly exotic sources like cosmic strings or phase transitions in the early universe. The study of gravitational waves has already begun to reveal unexpected aspects of black hole physics and stellar evolution. The masses and spins of black holes detected through gravitational waves often differ from those predicted by stellar evolution models, suggesting that our understanding of how massive stars end their lives requires significant revision. Some detected black holes fall into a mass gap, where theoretical models predict few objects should exist, challenging our comprehension of stellar collapse and black hole formation. Neutron star mergers observed through gravitational waves provide laboratories for studying matter under the most extreme conditions of density and pressure found anywhere in the universe. The detailed waveforms from these events contain information about the equation of state of nuclear matter, helping to resolve fundamental questions about the behavior of matter when atomic nuclei are compressed beyond their normal limits. The polarization of gravitational waves carries additional information about their sources and the nature of gravity itself. Unlike electromagnetic waves, which can be polarized in any direction perpendicular to their propagation, general relativity predicts that gravitational waves should exhibit only 2 specific polarization states. Precise measurements of gravitational wave polarization could reveal deviations from Einstein's theory or evidence for alternative theories of gravity. Population studies of gravitational wave sources are beginning to reveal the cosmic history of black hole and neutron star formation. The rate of detectable mergers provides constraints on the initial mass function of stars, the efficiency of binary evolution, and the role of stellar winds and supernova explosions in shaping the properties of compact object binaries. These observations offer new perspectives on fundamental questions about stellar physics and galactic chemical evolution. Gravitational wave astronomy also provides unique opportunities to test fundamental physics in regimes that cannot be accessed by any other means. The strong gravitational fields and high velocities present during black hole mergers create natural laboratories for testing general relativity, searching for violations of Lorentzian variance, and constraining alternative theories of gravity. Each new detection adds to humanity's understanding of the fundamental laws that govern the cosmos. The integration of gravitational wave observations with traditional electromagnetic astronomy, known as multi-messenger astrophysics, promises to revolutionize our understanding of cosmic phenomena. By combining the complementary information provided by gravitational waves, electromagnetic radiation, and high-energy particles such as neutrinos, astronomers can construct complete pictures of cosmic events that would be impossible to achieve with any single observational technique. As gravitational wave detectors become more sensitive and numerous, they will begin to detect a continuous background of gravitational radiation from countless unresolved sources throughout the universe. This stochastic gravitational wave background, analogous to the cosmic microwave background in electromagnetic astronomy, could provide information about the very early universe, including possible signatures of cosmic inflation or other exotic processes that occurred in the first moments after the Big Bang. The technology developed for gravitational wave detection has applications far beyond astronomy, contributing to advances in precision measurement, laser physics, and vibration isolation. The extreme sensitivities required for detecting space-time ripples have pushed the boundaries of experimental technique, leading to innovations that benefit many other fields of science and technology. As we contemplate these ripples in the fabric of space-time itself, we witness the universe communicating through its most fundamental medium, the geometry of space and time. Gravitational waves represent information in its purest form, disturbances in reality itself, that carry the stories of cosmic catastrophes across billions of years and trillions of miles to reach our In the gentle oscillations of laser light within kilometer-scale interferometers, we hear the universe speaking in a voice that remained silent throughout human history until just a few years ago. These waves reveal that space and time are not passive backdrops for cosmic events, but active participants in the drama of stellar evolution, black hole formation, and galactic development. Though invisible to our eyes, gravitational waves ripple through the cosmos, tracing the most violent events in space, while carrying information about cosmic phenomena that no other form of radiation can reveal. In their passage through our detectors, they remind us that the universe remains full of surprises, that reality operates on principles so subtle and elegant that a century of technological development was required to confirm their existence, and that the cosmos continues to unveil new ways of understanding the fundamental nature of existence itself. In the vast architecture of the cosmos, between the glittering islands of galaxies that contain billions of stars, there stretch regions of space so empty, so devoid of ordinary matter, that they challenge our understanding of nothingness itself. These are the cosmic voids. Immense volumes of space where galaxies are rare or entirely absent, creating a cosmic web of emptiness that spans hundreds of millions of light years and contains less than 10% of the universe's normal matter. The discovery of cosmic voids emerged gradually from large-scale galaxy surveys that mapped the three-dimensional distribution of galaxies throughout the nearby universe. As astronomers plotted the positions of thousands, then millions of galaxies, they expected to find matter distributed more or less uniformly throughout space, with only small variations in density. Instead, they discovered that galaxies are arranged in a complex network of filaments, sheets, and clusters, separated by enormous regions that are almost completely empty of luminous matter. The first major cosmic void to be identified and studied in detail was the Boötes void, discovered in 1981 through systematic mapping of galaxy positions in the direction of the constellation Boötes. This supervoid, sometimes called the Great Nothing, spans approximately 330 million light-years in diameter and contains remarkably few galaxies. So few that if Earth were located at the center of the Bootes void, astronomers would not have discovered the existence of other galaxies until the 1960s, fundamentally altering the development of cosmology and our understanding of the universe's structure. Within the Bootes void, the density of galaxies is less than 10% of the cosmic average, creating a region of space that approaches the emptiness of intergalactic space itself. The few galaxies that do exist within this supervoid are typically small, dim, and widely separated, struggling to form stars in an environment depleted of the gas and dark matter necessary for active galaxy formation and evolution. The formation of cosmic voids is intimately connected to the growth of large-scale structure in the universe through gravitational instability. In the early universe, small density fluctuations in the distribution of dark matter began to grow under their own gravity, with denser regions attracting more matter, while less dense regions became progressively more empty. Over billions of years, this process created the cosmic web we observe today, with matter flowing out of underdense regions toward the dense filaments and nodes where galaxies and galaxy clusters form. Cosmic voids are not completely empty, but contain a tenuous network of dark matter that provides the gravitational scaffolding for the large-scale structure of the universe. Computer simulations of cosmic evolution show that even the most empty voids retain a skeletal framework of dark matter filaments, though at densities far below the cosmic average. This dark matter structure influences the motions of the few galaxies that do exist within voids, creating subtle patterns that reveal the underlying gravitational architecture. The local void, also known as the Taurus void, lies relatively close to our own Milky Way galaxy and influences the motion of our local group through space. This nearby void spans approximately 150 million light-years and helps explain why our local cosmic neighborhood appears to be moving toward the Virgo cluster and other dense regions of the cosmic web. The gravitational influence of voids acts like cosmic vacuums, pushing matter away from their centers through a process called the Sunyaev-Zeldovich effect. Within cosmic voids, the physical conditions differ dramatically from those in the dense regions where most galaxies reside. The low matter density means that the few galaxies that do form within voids experience minimal gravitational interactions with neighbors, allowing them to evolve in relative isolation. These void galaxies often exhibit unusual properties, including active star formation, low metallicity, and undisturbed morphologies that preserve information about their early formation history. The study of void galaxies provides unique insights into galaxy formation and evolution in environments that approximate the conditions of the early universe. Without the disruptive influence of galaxy mergers and strong tidal forces, void galaxies may represent examples of how galaxies would evolve if left undisturbed for billions of years. Their low metallicity and active star formation suggest that they have evolved more slowly than galaxies in denser environments, making them cosmic fossils that preserve information about primordial galaxy formation processes. Cosmic voids also play important roles in the expansion history of the universe and the nature of dark energy. The acceleration of cosmic expansion, driven by dark energy, is most apparent in the largest and emptiest regions of space, where matter density is lowest. Void regions expand faster than the cosmic average, creating an asymmetric pattern of expansion that influences the overall geometry of space-time on cosmological scales. The Shapley void, one of the largest known cosmic voids, spans over 1 billion light-years in diameter and represents one of the most extreme examples of cosmic emptiness. This immense region contains virtually no galaxies and exerts a significant gravitational influence on the surrounding cosmic web. The existence of such enormous voids challenges our understanding of structure formation in the early universe and places constraints on cosmological models and the properties of dark matter. Temperature measurements within cosmic voids reveal that these regions are not completely cold, but maintain temperatures of several million degrees due to shock heating from cosmic structure formation. As matter flows out of voids toward denser regions, it creates shock waves that heat the remaining gas to high temperatures, making void regions detectable through their X-ray emission and their influence on the cosmic microwave background radiation. The cosmic microwave background shows subtle temperature variations that correspond to the locations of cosmic voids and overdense regions, providing a snapshot of the density fluctuations that existed when the universe was only 380,000 years old. These observations confirm that cosmic voids are ancient features that have been growing and evolving since very early in cosmic history, expanding and emptying as matter flows toward regions of higher density. Neutrinos, nearly massless particles that interact very weakly with ordinary matter, may play important roles in the evolution of cosmic voids. Because neutrinos travel at nearly the speed of light and interact gravitationally but not electromagnetically, they can stream freely out of underdense regions, carrying energy and momentum that influences the growth rate of cosmic structures. The detection of neutrino mass through cosmological observations may depend partly on measurements of void properties and their evolution over cosmic time. The distribution and sizes of cosmic voids provide powerful tests of cosmological models and the nature of dark matter. Cold dark matter simulations predict specific patterns of void formation and evolution that can be compared with observations. Alternative theories such as warm dark matter or modified gravity models predict different void properties, making cosmic voids important laboratories for testing fundamental physics on the largest scales. Void statistics, measurements of void sizes, shapes, and number densities, are becoming increasingly important tools in precision cosmology. Large-scale galaxy surveys can measure void properties with sufficient accuracy to constrain cosmological parameters, such as the matter density, dark energy equation of state, and neutrino masses. These measurements complement other cosmological probes and provide independent confirmation of the standard model of cosmology. The largest cosmic voids may represent the most pristine examples of the universe's initial conditions, regions where the density contrast has grown primarily through gravitational evolution without significant modification by astrophysical processes. Unlike dense regions where galaxy formation, stellar feedback, and active galactic nuclei can significantly alter the matter distribution, voids remain largely unaffected by such processes, preserving information about the primordial density field. Cosmic void surveys require sophisticated observational techniques to map the three-dimensional distribution of galaxies with sufficient completeness and accuracy. Modern spectroscopic surveys measure distances to millions of galaxies by analyzing the redshift of their light, creating detailed maps of cosmic structure that reveal void boundaries and internal structure. These surveys must account for observational biases and selection effects that can artificially create apparent voids in regions where galaxies are too faint to detect. The future of void cosmology lies in next-generation surveys that will map billions of galaxies across cosmic time, revealing how void properties have evolved since the universe was young. The Vera C. Rubin Observatory, AK space mission, and other planned facilities will create unprecedented maps of cosmic structure that will transform our understanding of void formation, evolution, and their role in cosmic acceleration. Theoretical models of cosmic voids must account for the complex interplay between dark matter, ordinary matter, and dark energy across a wide range of scales. Sophisticated computer simulations that include both gravitational dynamics and astrophysical processes are required to predict void properties accurately and interpret observational results. These simulations reveal that voids are dynamic, evolving structures that grow and merge over cosmic time, creating an ever-changing pattern of cosmic emptiness. The philosophical implications of cosmic voids extend beyond their scientific importance to questions about the nature of existence and nothingness. These vast regions of space challenge our intuitive understanding of emptiness and vacancy, revealing that even the most apparently empty regions of the universe contain dark matter, radiation, and the fabric of space-time itself. True emptiness, if it exists at all, may be a more subtle and complex concept than our everyday experience suggests. As we contemplate these immense regions of cosmic emptiness, we encounter the universe's tendency toward organization and structure, operating on the largest possible scales. Cosmic voids are not random empty spaces, but integral components of the cosmic web, shaped by the same gravitational forces that create galaxy clusters and filaments. They represent the universe's breathing spaces, regions where expansion dominates over gravitational collapse. and where the influence of dark energy is most apparent. In the gentle expansion of cosmic voids, we witness the universe's fundamental asymmetry between matter and emptiness, between the crowded neighborhoods where galaxies cluster together and the vast, quiet regions where space itself becomes the dominant presence. These voids remind us that the cosmos operates on scales so large that entire galaxy clusters become mere points of light, and emptiness becomes a cosmic phenomenon worthy of study and contemplation. In the emptiness between stars and galaxies, there is silence. But even in the void, there is meaning. The profound significance of space itself as an active participant in cosmic evolution, expanding and cooling, and carrying within its geometric structure the history and future of all existence. The voids teach us that nothingness itself can be beautiful, mysterious, and full of information about the deepest workings of the universe. In the deepest contemplation of cosmic time, where billions of years compress into moments and the entire history of the universe unfolds like chapters in an endless book, we arrive at perhaps the most profound question that consciousness can ask. What is the ultimate destiny of everything that exists? The fate of the universe represents the final phenomenon we can explore, not a single event or object, but the slow, majestic conclusion to the greatest story ever told. The gradual transformation of all matter, energy, and space-time itself toward their ultimate destiny. Current observations and theoretical understanding point towards several possible endings for our cosmos, each more extraordinary than the last, each operating on timescales so vast that they reduce the entire history of stars and galaxies to brief, flickering moments in an almost incomprehensibly long cosmic twilight. These scenarios, heat death, the Big Rip, the Big Crunch, or cyclic renewal, represent the final chapters in the universe's biography, written in the language of thermodynamics, quantum mechanics, and the mysterious force we call dark energy. The most widely accepted scenario for the universe's future is thermal equilibrium, often called the heat death of the universe. This gentle ending emerges from the second law of thermodynamics, which dictates that entropy, the measure of disorder in any system, always increases over time. As the universe continues to expand and cool, energy gradually spreads out more and more evenly throughout space, reducing the temperature differences that drive all processes, from stellar fusion to the complex chemistry of life. In this distant future, perhaps 10 to the 100 years from now, the last stars will have exhausted their nuclear fuel and faded to cold, dark remnants. The universe will consist primarily of black holes, neutron stars, white dwarfs, and the scattered debris of dead stellar systems, all gradually cooling toward absolute zero as the cosmic expansion carries them ever farther apart. Even the most massive black holes will eventually evaporate through Hawking radiation, though this process will take times so long, 10 to the 100 powers years for the most massive black holes, that they dwarf the current age of the universe by factors beyond human comprehension. Yet even in this far future, the universe will not be completely static. Virtual particles will continue to pop into existence and annihilate in the quantum foam of space-time, and over truly astronomical timescales, 10 to the 10 to the 56 years, quantum tunneling events may spontaneously create new particles and even brief instances of complex structure. These quantum fluctuations represent the universe's final, faint heartbeat, persisting long after all the stars have died and all the black holes have evaporated. The Big Rip scenario presents a more dramatic ending, driven by the accelerating expansion of space itself. If dark energy continues to strengthen over time, or if it represents a form of energy density that increases as the universe expands, the expansion rate could eventually become so rapid that it overcomes all other forces in nature. In this scenario, occurring perhaps 22 billion years from now, the fabric of space-time itself would expand so quickly that it would tear apart all bound structures in the universe. First, galaxy clusters would be pulled apart as space expands faster than gravity can hold them together. Then, individual galaxies would be shredded, their stars scattered into the growing void. Next, stellar systems would be disrupted as expanding space overcomes the gravitational bonds between stars and planets. Finally, in the last moments before the Big Rip, atomic nuclei themselves would be torn apart, as space-time expansion overwhelms even the strong nuclear force that holds protons and neutrons together. The Big Rip represents the ultimate victory of space over matter, a scenario where the geometric expansion of the universe becomes so extreme that it destroys not just the structures built by gravity, but the very possibility of structure itself. In the final fraction of a second, as space-time expansion approaches infinite rate, even the concepts of distance and time would lose their meaning in a universe where space itself becomes the destroyer of all that exists. The Big Crunch offers a different kind of ending, one where gravity ultimately triumphs over cosmic expansion. If the universe contains enough matter and energy to eventually halt and reverse its expansion, all the matter in the cosmos would begin falling back together in a cosmic collapse that mirrors the Big Bang in reverse. Galaxies would merge and coalesce, stars would be disrupted by tidal forces, and eventually all matter would compress back into the infinitely dense, infinitely hot state from which the universe began. Current observations suggest that the Big Crunch is unlikely, as measurements of cosmic acceleration indicate that dark energy is driving the expansion to accelerate rather than decelerate. However, if dark energy represents a temporary phase in cosmic evolution, or if our understanding of gravity on cosmic scales is incomplete, the universe's expansion could eventually slow, stop, and reverse, leading to a symmetric ending that returns all existence to its primordial state. The cyclic universe models present perhaps the most intriguing possibility, that the death of our universe might be simultaneously its rebirth. In these scenarios, the Big Crunch is followed immediately by a new Big Bang, creating an endless cycle of cosmic death and renewal that has repeated countless times in the past and will continue forever into the future. Each cycle might last hundreds of billions of years, with the collapse and re-expansion of space-time creating an eternal rhythm of cosmic breathing. String theory and other advanced theories of quantum gravity suggest mechanisms by which a collapsing universe might bounce back into a new expansion phase, avoiding the infinite densities and temperatures that mark the classical Big Bang and Big Crunch. These models predict that information from previous cosmic cycles might persist through the bounce, creating connections between successive universes that share common physical laws and perhaps even common structures. The concept of cosmic inflation, which describes the rapid expansion of space in the first fraction of a second after the Big Bang, might also play a role in the universe's ultimate fate. If inflation is an ongoing process that creates new regions of space-time containing independent universes, our cosmic death might be accompanied by the birth of countless new cosmos, each with their own physics, their own stars and galaxies, and perhaps their own forms of consciousness contemplating their own cosmic destinies. On more modest timescales, the fate of specific cosmic structures tells stories of transformation rather than absolute ending. Our own Milky Way galaxy will collide and merge with the Andromeda galaxy in approximately 4.5 billion years, creating a new, larger galaxy that astronomers have nicknamed Milkomeda. This galactic collision will be a spectacular reorganization of hundreds of billions of stars. But it will not mark an ending so much as a transformation, the birth of a new cosmic structure from the marriage of two ancient ones. Our Sun, the source of energy that enables all life on Earth, will exhaust its hydrogen fuel in approximately 5 billion years, beginning its evolution toward a red giant star that will engulf the inner planets before finally shedding its outer layers to become a white dwarf. The death of our star will mark the end of the solar system as we know it, but it will also contribute heavy elements to the interstellar medium, providing raw materials for future generations of stars and planets. The local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, will gradually merge into a single massive galaxy over the next 100 billion years. This cosmic consolidation will occur as the expansion of space carries more distant galaxy groups beyond the gravitational reach of our local environment, leaving the merged local group as an island universe, surrounded by an ever-expanding ocean of empty space. Even within these far future timescales, life and intelligence might find ways to persist and evolve. Advanced civilizations could potentially harness the energy from black hole evaporation, stellar remnants, or even the expansion of space itself, to maintain complex structures and information processing capabilities. The prospect of intelligence surviving and adapting to the changing cosmos raises profound questions about the ultimate purpose and meaning of cosmic evolution. Quantum mechanics introduces additional uncertainty into predictions about the universe's fate. The possibility of vacuum decay, a quantum transition to a lower energy state that could propagate throughout space-time at the speed of light, represents a potential ending that could occur at any moment or never. If our universe exists in a metastable vacuum state, quantum fluctuations could trigger a transition that would fundamentally alter the laws of physics everywhere, effectively ending the universe as we know it, while potentially creating new forms of existence governed by different physical principles. The anthropic principle suggests that the ultimate fate of the universe might be connected to the existence of observers capable of contemplating that fate. Some interpretations of quantum mechanics propose that conscious observation plays a fundamental role in determining physical reality, raising the possibility that the continued existence of intelligence might influence the universe's evolution in ways we cannot yet understand. The concept of the omega point, proposed by mathematical physicist Frank Tipler, envisions a far future where intelligent beings have gained control over all matter and energy in the universe, creating a state of infinite information processing capacity and computational power. In this scenario, the apparent ending of the physical universe becomes the beginning of a new form of existence based on pure information and consciousness. Recent discoveries about dark matter and dark energy remind us that our understanding of the universe's composition and dynamics remains incomplete. These mysterious components, which together comprise 95% of all existence, could behave in unexpected ways that dramatically alter predictions about cosmic fate. New physics operating on cosmic scales might reveal possibilities for the universe's future that are currently beyond our imagination. The study of cosmic fate also illuminates the deep connections between the largest and smallest scales of existence. The quantum properties of elementary particles, the thermodynamics of black holes, and the geometry of space-time all contribute to determining how the universe will end. These connections suggest that understanding cosmic destiny requires a unified theory of physics that seamlessly connects quantum mechanics, general relativity, and thermodynamics into a single, coherent description of reality. As we contemplate these vast timescales and cosmic endings, we encounter a profound meditation on the nature of permanence and change. Every star, every galaxy, every black hole, and even space-time itself exists within the flow of cosmic time toward an ultimate transformation. Yet within this apparent impermanence, we find the seeds of permanence. The conservation laws, physical constants, and mathematical relationships that persist even as the structures they govern evolve and change. The universe's fate reminds us that existence itself is a temporary arrangement of matter and energy, a brief flowering of complexity within the cosmic expansion toward equilibrium. Yet this temporary nature does not diminish the significance of cosmic evolution, but rather enhances it by highlighting the extraordinary improbability and preciousness of the structures and processes that enable stars to shine, planets to form, and consciousness to emerge. Perhaps the most profound insight emerging from our contemplation of cosmic fate is that endings and beginnings are not opposite concepts, but different aspects of the same fundamental process of transformation. The death of massive stars enables the birth of new stellar generations. The collision of galaxies creates new cosmic structures. The evaporation of black holes returns matter and energy to the vacuum from which new particles might emerge. In the context of cosmic time, all the phenomena we have explored, the birth of stars in nebulae, the spectacular deaths of supernovae, the mysterious presence of black holes and dark matter, the patient pull of the Great Attractor, the brilliant light of quasars, the ripples of gravitational waves, and the vast emptiness of cosmic voids. All of these represent moments in the universe's long journey toward its ultimate destiny. As the universe stretches into its far future, we rest beneath its stars, knowing that our moment of existence coincides with a remarkable epoch in cosmic history. A time when stars still shine, when galaxies still form and evolve, when the cosmos remains filled with light and motion and the endless dance of matter and energy. We are witnesses to the universe during its youth, observers of cosmic phenomena that will gradually fade and transform as the eons pass. Even the universe's grandest phenomena must eventually fade, but in their passing the universe remains a wonder. The slow expansion toward heat death, the dramatic possibility of the Big Rip, the symmetric return of the Big Crunch, or the eternal renewal of cyclic cosmos. Each potential ending carries within it the seeds of meaning and beauty that have characterized cosmic evolutions since the beginning of time. In the silence of the far future, when the last black holes have evaporated and the final particles have decayed, when space-time itself approaches its ultimate equilibrium, the universe will remain as it has always been. A stage for the unfolding of existence, a canvas upon which the laws of physics paint their eternal masterpiece. A cosmic poem written in the language of matter and energy, space and time, consciousness and contemplation. As our cosmic journey draws to its gentle close, and the vast panorama of galactic phenomena slowly fades into the peaceful darkness of approaching sleep, we find ourselves transformed by our passage through the universe's most magnificent and mysterious realms. We have traveled from the stellar nurseries where new suns are born to the distant future, where the cosmos itself will undergo its final transformation. In this passage through space and time, we have encountered beauty, mystery, and wonder on scales that stretch our imagination to its limits, while simultaneously revealing our profound connection to the cosmic story that continues to unfold around us. In the nebulae, we witness the patient creativity of the universe, where gas and dust condense over millions of years to ignite the nuclear fires that will burn for billions more. These stellar birthplaces reminded us that creation is not a single moment, but an ongoing process, a cosmic meditation on the transformation of simplicity into complexity. Through the spectacular violence of supernovae, we observed how stellar death becomes the catalyst for new life, how the explosive end of massive stars enriches the cosmos with the heavy elements that make planets and biology possible. In these cosmic catastrophes, we found not destruction, but transformation, the universe's way of recycling matter and energy to enable ever greater complexity and beauty in future generations of stars and worlds. The black holes showed us the ultimate expression of gravity's power, where matter and energy approach the very limits of physical existence. These cosmic beasts, though invisible to our eyes, shape the architecture of galaxies and remind us that the universe operates according to principles so fundamental and profound that even light itself cannot escape their influence. In their patient consumption of matter and space, we glimpsed the universe's capacity for both creation and dissolution, the eternal dance between existence and void. Dark matter revealed the humbling truth that most of the universe remains invisible to our direct perception, yet profoundly influences everything we can observe. This cosmic scaffolding, holding galaxies together and guiding the formation of large-scale structure, taught us that reality extends far beyond the boundaries of our immediate experience, that the cosmos contains depths of mystery that challenge our understanding, while supporting our very existence. The Great Attractor pulled us into contemplation of forces operating on the largest conceivable scales, where entire galaxy clusters flow like rivers toward massive concentrations of matter hundreds of millions of light-years away. In this cosmic current, we felt the universe's fundamental interconnectedness, the way gravity weaves space and time into a unified tapestry where every object influences every other across the vastest distance. Quasars transported us to the most energetic phenomena in the cosmos, powered by supermassive black holes that convert matter into energy with stunning efficiency. These cosmic lighthouses, visible across billions of light-years, illuminated the universe's violent youth while demonstrating the extraordinary power that emerges when matter falls toward the ultimate gravitational abyss. The rogue planets reminded us that worlds can exist in the most unexpected places, wandering the cosmic deep without the warming light of a parent star. These lonely travelers expanded our conception of where life and complexity might emerge, suggesting that the universe's creativity extends even into the dark spaces between stellar systems. Gravitational waves introduced us to an entirely new way of listening to the cosmos, detecting ripples in space-time itself that carry information about the most violent events in the universe's history. Through these cosmic tremors, we learned that space and time are not passive backgrounds for cosmic events, but active participants in the drama of existence, capable of vibrating with the echoes of distant catastrophes. The cosmic voids showed us that emptiness itself can be a cosmic phenomenon worthy of study and contemplation. These vast regions of space, nearly devoid of galaxies, revealed the universe's web-like structure, while reminding us that nothingness and somethingness are not opposites, but complementary aspects of cosmic architecture. Finally, our contemplation of the universe's ultimate fate connected us to the deepest questions about existence, permanence, and transformation. Whether the cosmos ends in heat death, the Big Rip, the Big Crunch, or eternal cycling, we discovered that endings and beginnings are aspects of the same fundamental process of cosmic evolution that has been unfolding since the universe began. Throughout this journey, we have been reminded again and again that we are not separate from the phenomena we have explored, but intimately connected to them. The atoms in our bodies were forged in the nuclear furnaces of ancient stars. The calcium in our bones was created in stellar explosions that occurred billions of years ago. The iron in our blood was scattered through space by supernovae that enriched the cosmos with the elements essential for life. We exist because the universe has spent nearly 14 billion years creating the conditions necessary for stars, planets, and ultimately biology to emerge and flourish. Our consciousness represents the cosmos becoming aware of itself, the universe developing the capacity to contemplate its own existence and wonder at its own beauty and mystery. As you drift towards sleep, carried by the gentle rhythm of cosmic time, remember that you are participating in the greatest story ever told. The story of matter and energy, space and time, organizing themselves into ever more complex and beautiful forms. From the first moments after the Big Bang to the formation of the first atoms. From the birth of the first stars to the assembly of galaxies. From the emergence of heavy elements to the formation of planets. From the first stirrings of life to the development of consciousness capable of contemplating the cosmos itself. You are the universe thinking about itself. Your thoughts, your dreams, your capacity for wonder and contemplation represent the cosmos achieving self-awarenessness through the intricate dance of atoms and molecules, cells and neurons that make up your being. In your consciousness, the universe experiences beauty, mystery, and meaning that would not exist without the remarkable accident of complexity that led to your existence. The phenomena we have explored tonight will continue their ancient work while you sleep. Stars will continue their nuclear burning, black holes will continue their patient consumption of matter, dark matter will continue its invisible influence on cosmic structure, and gravitational waves will continue to ripple through space-time, carrying news of distant cosmic events. The universe will continue its expansion, its cooling, its gradual evolution toward whatever ultimate destiny awaits. Yet in this moment, as you rest beneath the stars, you are connected to all of these processes through the fundamental forces and particles that compose your being. You are stardust contemplating stars. Cosmic matter organized into a form capable of wonder and appreciation for the beauty and mystery of existence itself. The universe is vast beyond human comprehension, ancient beyond human experience, and filled with phenomena that challenge our understanding and inspire our imagination. Yet it is also intimate and personal, expressing itself through the patterns of your thoughts, the rhythm of your breathing, the gentle descent into sleep that mirrors the cosmic expansion toward equilibrium and peace. As the galaxies turn in their slow celestial dance, as black holes whisper their gravitational songs across the void, as the cosmic web continues its patient expansion through space and time, you rest in the knowledge that you are part of this magnificent story. Your existence adds meaning to the cosmos, just as the cosmos adds meaning to your existence. Sleep now in the gentle embrace of cosmic time, where moments become eons and eons become moments, where the boundary between self and universe dissolves into the peaceful unity of existence contemplating itself. Let the rhythm of stellar birth and death, the pulse of gravitational waves, the slow breathing of cosmic expansion and contraction, carry you into dreams where the mysteries of the cosmos continue to unfold in the theater of your imagination. The universe has been waiting 14 billion years for this moment, for matter to organize itself into a form capable of appreciation, wonder, and love for the cosmic story of which we are all a part. In your peaceful rest, the cosmos finds its meaning, its purpose, its greatest achievement in creating beings capable of contemplating beauty, seeking truth, and finding wonder in the magnificent, mysterious, ever-unfolding story of existence itself. As the universe stretches into eternity, we rest beneath its stars. In the silence, the galaxies turn, the black holes whisper, and the wonders of space endure, forever unfolding, forever beautiful, forever filled with the promise that consciousness and cosmos, matter and meaning, existence and wonder will continue their eternal dance through the vast, magnificent, mysterious depths of space and time.